Welcome to the Net Zero Emissions Workshop today. It's organized by SDG Europe Regional Advisory Committee. This is the second Net Zero Emissions Workshop. The first one we ran in 2021 last year. It was a 3-day workshop. It was concentrated mainly on the idea, on the 3-day workshop then was mainly the idea, was then the geophysical, technical background of it, the monitoring of the stores, and monitoring solutions, but also the regulation part of it and the monitoring regulations at the end of the third day. So this is a continuation of that workshop, and here today we would like to look at some of the examples of the business cases, how companies do in this difficult environment. So there's been several projects up and running, but there is almost like a waiting period and see what happens next, and then see how companies are doing, how they're taking the carbon capture projects into the future, so to get around that, ideas on that, but also to look at some of the monitoring solutions. So we, what's the aim around it, right? So the EU aims to be the first climate neutral continent with the net zero greenhouse gas emissions achieving this by 2050, to go net zero by 2050. To get to this target, all members of the EU are pledged to reduce emissions by at least 55% by 2030 compared to 1990 levels, or the ones set by the local government to achieve this. So reaching these targets will require actions by all sectors of the economy within EU, and but CCS, carbon capture, is a cross-sector solution, which is essential to achieving this climate neutrality for many other sectors as well. So low carbon hydrogen production is enabled by CCS, which is enabled by CCS, also has the potential to decarbonize these sectors in addition to reducing emissions and from the heating and transport sectors. And also CO2 can also be reused as a component when producing, for example, industrial use, producing concrete, steel, and other biofuel or other products. Renewables. From what we see in renewables, nuclear power and energy efficiency, which is advocated, they are very important, but they will not be enough to reach the climate neutrality. The CCS will be essential in ensuring that the power generation and industrial processes are secure, reliable, and sustainable for people living in the EU and in the whole world. Achieving net zero emissions through CCUS provides us with possible offset solutions as well for some of the other sectors where we struggle with to find alternative solutions to decarbonize the environment. CCS, carbon capture, is a 3-part chain. So we've got the capture part of it, we've got transportation capture with CO2, and then we've got transportation part and storage part. So that capture is it's captured at the power plants, installations, industries, combustion of fossil fuels, and biomasses. It can also be within industry sectors, steel, ammonia, cement, and others. And of course, from hydrogen manufacturing, either it's electrolysis, but it's so far uneconomic due to the high energy demand in the process. And also from breakdown to hydrogen and CO2 from methane. So then we capture the CO2 from there. And also, in the distant future, I guess we can implement the removal from the CO2 from atmosphere as a direct capture methods. That's the capture part of it. The transportation part of it is equally important. We can reuse the existing infrastructure that gives us the opportunity, especially in the areas where we have existing high-density existing oil and gas infrastructure. We can reuse that, but also to take into the future all the infrastructure which is capable of transporting hundreds of millions of tons of CO2 per year. There is a long lead time in this installation and manufacturing of the required equipment, and that development should begin quite quickly now. And of course, what we concentrate mainly on is the storage part of it. Is monitoring of the performance at all phases of the CO2 reservoir's life, its identification, injection, closure part of it, but also any movement in the catwalk. We use different methods for monitoring. We use pressure, temperature changes within the well, seismic monitoring, well observations, and of course monitoring of the environment of the nature as well. If we look at the historical CO2 emissions, this is the graphs from select countries in Europe for the last 100 years, showing the average emissions per country. So we can see that they increase, but they are almost like on a decreasing level towards from 1960s and onwards. But they are on a higher level compared to, for example, 100 years ago. So what is, if we look then at more distribution of the projects that we actually run. So if you remember these numbers here, so this is what we produce, right? So Norway is about 45-40 million tons of CO2 per year, and Sweden is down there. But of course, if you do Germany, it's over 500 million CO2 tons per year. Look at the projects that we are doing, so this to be in perspective. So IGP IGP mentions that they have total 65 projects for CCS in Europe. Actually, when I look at the statistics from last year when we had run this workshop, it was 30 projects, so it's good it's going up. So the map on the left-hand side, created by Zero Emissions Platform, shows various CCS projects, not only storage and transport, but also the capture project, various phases of CO2. And there are 67, 65 projects here shown on this map. If I then show the statistics of the times and the amount of CO2 injection, capture and injection per year for these projects. So you see, look at the numbers. For example, one of the largest projects will be the Smehe in the North Sea. Also, we look at some other projects as well, but they expand into 25, almost 27. So then you can reflect back to the numbers on the previous slides, the amount of actual emissions we produce. We need to combine all the different activities with the CO2 capture to achieve this net zero emissions. So also it's important, would like to mention as a part of the workshop is the carbon capture bid round. For example, in the UK, they have it was an invite from North Sea Transition Authority, invite for UK's first ever carbon storage licensing round with 30 potential areas. The new areas are alongside with existing 6 licenses, and they're built to make a significant contribution towards the storage and large carbon dioxide volumes on the UK sector. This is something interesting for that sector. Back to the workshop. So we have several presentations per day. This is like we start pretty much now, and then the first presentation will be by Katarina Kuna, presenting the role of geophysics in the Northern Lights, and then we go on with the program afterwards. I would also like to thanks to the organizers of the workshops. We've got Anthony Price from Total Energies, Adriana Ramirez from TGS, Fiona Sutherland from Storegga, and Benjamin Birol from DPR, Shiv Dasgut SCG, and Babozole from Thanks, Lori, to you for organizing the workshop and for making all the practical part working. And yes, I'll stop sharing here, and then we can take the Katarina's presentation first. Right.
So first of all, I have COVID. So if I'm a bit sniffly and a bit slow, you have to forgive me and bear with me. Second, it says in the table that my affiliation is Shell. It is, but it's not. I mean, I am Shell, but I'm seconded to the Northern Lights JV and contracted back to Equinor. So I have 3 hats. Depending on the situation, I have to put one or the other. Here I have my Northern Lights hat. And although many of you probably have seen many presentations about what is the role of the geoscience community in the energy transition and specifically in the CCS, what I'm going to show here is specifically about geophysics. And I'm not going to show what we think it could be, but our actual experience in the Northern Lights, which it's been a 4 years, 5 years experience. Therefore, you will be able to tell yourself if we have a predominant role or not in the CCS world. This is work that has been done in the subsurface team in the Northern Lights project, by the way. So the Northern Lights, it's not a CCS project or a company, which is a JV now. It's a CO2 transport and storage company, which means that we transport let me put it in, yeah. We transport the CO2 from the emitters that capture it themselves in some parts of Europe and Norway. We transport it by specialized vessels into a receiving terminal in Øygarden, south of Bergen. And then we transport it via pipeline to the permanent storage. And what I'm going to talk about is that permanent storage, because that's where we have something to say about. And that permanent storage is a storage complex, and it's a storage site, and it's called Aurora. Aurora is 100 kilometers offshore, 2,700 meters deep, and is an open saline aquifer located on the slopes of the Troll structure. The primary storage units are Cook and the Johansen Formation, and they are shallow marine Jurassic sands. And the secondary storage unit is the Staffjord Formation, which is not an injection unit, it's just a unit in case that the CO2 migrates into it, then it's not considered a leakage, it's considered just part of the storage. The primary seal is called the Drake Formation, and it's a thick package of deep water shales. And we also are lucky to have a secondary seal, which is the BCU, or the Base of Cretaceous Unconformity, which is also the seal of the Troll field, so we know it works. The Aurora storage, is a storage capacity or injection capacity, is divided in two. Phase 1 is 37.5 million tons that are going to be injected in this well, the EOS injector. And there is a contingent well as well, in case that the EOS injector doesn't work. And the EOS sidetrack injector is going to be drilled this year, and the contingent injector is going to be drilled this year as well. Phase 2 is what's coming next. It's 100 million tons in 3 wells that we are planning at the moment. The injection rates are the same for all of them, 1.5 million tons per year on a time period of 25 years total. So to understand what is our role as geophysicists in the CCS world, we have to understand what are the subsurface accountabilities within the core activities for CO2 storage assessment. So we have 3 of them. The first one is the storage resources and scalability. It's basically how much we can store safely. That helps us to build the commercial commitments. Then we have a very important one, which is the risk assessment of this storage, and that leads to the containment risk assessment. And after you've analyzed what are the risks, you have to come up with a risk mitigation plan. And what most of people hear about geophysics having a role in CCS is the measure, monitoring, and verification plan, which is the seismic monitoring. But I hope I can show you at the end of this presentation that's not all what we will do or that we do. So let's start with the first role, which is the storage resources. It all starts with a portfolio screening, just very similar to what we do in exploration in the oil and gas business. But in this case, we go and analyze different storage sites. And this is an example of the CO2 atlas in the NPD. We have abandoned and depleted hydrocarbon fields. That's one of the storages that we could have, and we could also have saline aquifers. So you do a screening of them, and for that you need seismic, 3D, 2D, and then you need to do quantitative interpretation of that seismic. Once you've done some regional seismic interpretation, with that you do a ranking of these storage options, and you come up with your favorite candidates. To de-risk those favorite candidates, you have to do a little bit more of seismic interpretation, more quantitative interpretation, and you have to determine whether it's feasible to do monitorability. If you do all this work properly, then you come up with one candidate for which you might have to do an exploration or appraisal well, which is the case that we had, because we thought a saline aquifer was our top option, and we had to then put an exploration appraisal well on it. But if your top option is a depleted hydrocarbon field, hello? Is there a question? No. If your option is a depleted hydrocarbon field, then you might have to do further studies. If you have to put a well in it, then you're going to have to do borehole geophysics. You have to do site survey analysis, geohazards, and more seismic interpretation. So once you've had your top site and you've done your well and your further studies, then it comes our bread and butter. This is the bread and butter of geophysicists in the oil and gas business. But it's going to be your bread and butter too in the CCS business, which is the reservoir characterization, whereby you go into the seismic in depth, you map your storage complex detail with the most detail you can, and then you look for all those depositional features that can have an impact in your CO2 plume migration or behavior. In this case, I'm showing one of the features that we found using various attributes. In this case, it's a spectral decomposition. You can also see it in the seismic. And in the end, we came up with this huge corridor that we still don't know very well what it is. But that find help us to determine what was our best depositional concept. And this depositional concept is what you put then in your reservoir model. It's key to know what are these features that could have any kind of potential effect on the CO2 plume migration. Another important part of our aspect of our work is to do seismic modeling or inversion if you could. In this case, we couldn't. What we have here is an example of 2D seismic forward modeling just to find out, to have a narrowing down of what kind of properties. And in this case, we start with acoustic properties and we extrapolate to porosities if we can. To narrow down what are the properties that could be in those features for the reservoir modelers to put in the reservoir model. So key aspect of the CCS world is to understand what we have in the subsurface, and seismic and geophysics is, as you know, key to do that. Another important aspect is for the risk assessment. We need to find out how is the structural setting. We need to understand where are all the faults that could have an impact on the CO2 plume migration or behavior. We need to know where there is a juxtaposition of the storage complex with other unwanted stratigraphy. We don't want the CO2 to get out of the storage complex. So the mapping of the faults is extremely important, and you can do that only on seismic. Another thing that is important to do on seismic is the geohazard analysis. And that geohazard analysis could be for both, for the overburden to understand the pathways or the geological and well-related pathways where the CO2 can possibly migrate out of the storage complex, which is the key to the key input to the containment risk assessment, or it could be also for the wells and seabed facilities placement. So not just the overburden, but also the seafloor, again, is something that you do with seismic and you do as a geophysicist. Then it comes to what we all know that is an activity that geophysicists are going to have in the CCS world, which is the monitorability. Seismic in the Northern Lights project is the preferred method for monitoring where the CO2 plume is going to go. It's part of the regulation requirements. You cannot have a project if you don't demonstrate to the government that you have a monitorable storage complex. For that, you need to do some feasibility work. And this is an example of Anna Kari's work on demonstrated that you can actually see CO2 plume migration in the seismic at different stages of the injection. And this is what we did this year, is to plan the baseline survey that is going to be used for the monitorability, for the monitoring of both phases 1 and 2 for the well EOS and the contingent ad, as well as many other wells that can be put in the phase 2. This is the baseline that we acquired this year. This is how it looks into the operations. We finished the operations on June 8th. We had to plan this survey for a year. So there is a lot of not just the coordination, the planning and the survey design and the operations and the processing planning, that all of that gets where the geophysicists have a predominant role. So again, we are key for this activity. Another type of monitoring tool that we're going to use is the passive monitoring. It's basically to create a baseline for the natural seismicity before we have the CO2 injection. Because one thing we don't want is to have the CO2 injection to be the cause, or for people to think the CO2 injection is the cause of natural seismicity. And if that were to happen, then you could have a big risk of damage to the project reputation. You've seen what happened with Shell in Groningen in the Netherlands. So we don't want that. Passive monitoring is what is going to help us to achieve that goal, and that is through a consortium that is called HNet, that is right now in the making, or it's almost finalized, that is going to use some array of permanent onshore, semi-permanent of onshore stations, and hopefully we're going to be able to add also offshore stations, PRM stations, into this net to look for the potential natural seismicity happening in the area. Other monitorability or monitoring tools that were analyzed, one of them was gravimetric. It's like a no-brainer because we know that the seismic is good at detecting the presence of CO2, but not very good at discriminating what is the saturation. So if we were to have very thin layers where the CO2 is migrating really fast and it goes over the seismic, over the license border, we are not going to be able to see that with seismic, but we might be able to see it with gravity. That's what we thought. So Anna-Kari again did this work on the feasibility whether gravimetric measurements could help us. And yes, you can see the effect of gravity on CO2 migration. However, you can only see it when you have a very large volume of CO2 injected, which means that by the time we detect it, it might be too late and the CO2 might have migrated out of the license. Also, there was the additional complication that we have effects from the troll field that we didn't know how they were going to alterate these results. Therefore, this monitorability tool was not selected for the Northern Lights, but we did the feasibility study at least. There were other feasibility studies that were done for other monitoring tools, and I know that one of the talks today is going to be about CSEM. So we did look into CSEM because it would have been great to be able to monitor our injection with CSEM. Unfortunately, given the type of given the depth and the injection rates that we have, the type of saturation that we're going to have, we're not going to be able to discriminate the CO2 plume using CSEM. So this monitorability tool was not chosen into the plan. One tool that we really wanted to use was 3D VSP DAS. We would have saved us one repeat survey in around our well EOS. This is work that was done in Equinor, modeling the how we can use 3D VSP to illuminate our CO2 plume migration. Unfortunately, due to issues with the well hardware, let's put it in that way, we could not install these fiber optics in the wells that we have for phase one. However, this is ongoing. Another feasibility is ongoing for the wells that we're going to drill for phase two. Now, this is also the key, one of the key works that Anna-Kari is doing for the Northern Lights, which is the petroelastic model. So it's basically bringing the reservoir model into a geophysical understanding by inputting rock properties into this, specifically acoustic properties. And this is the type of model that you use to find out whether you're going to see the CO2 in the seismic. And this model is being updated at the moment because we have an update of the reservoir model. So watch the space, more to come. So with that, I'd like to come back to the first page, but instead of showing you all the other subsurface accountabilities, I want to show you what are we doing in the Northern Lights in terms of geophysics only. So for the storage resources and scalability, we're doing seismic interpretation, or we just finished a seismic interpretation, the thorough one that I talked about for reservoir characterization to be input into the model. We also did some the seismic forward modeling. The petroelastic model update is ongoing. The 4D baseline, we just finished it the operations finished, but the processing is going to be ongoing for the next year. So we have to keep a look on it. We have done and we will keep doing storage resources evaluation. What is to do a screening of all the portfolio of storage leads and prospects that we have in the EL001 area and beyond. Also, in terms of risk assessment, we're doing a lot of preliminary analysis for well and surface facilities placement for the phase 2 wells. We're going to have to do an update of all the seismic interpretation input into the containment risk assessment because of this. Because at the end of this year, we have to do an application for the injection permit to the Norwegian Environmental Agency. And we have to do a plan for the development of phase 2, the PDO. We have to then finish up the update of the CRA, our containment risk assessment, and an update of the storage complex monitoring plan, all because we have a new reservoir model. The MMMV is going to continue on the passive monitoring network follow-up. And as I mentioned before, we're doing the feasibility study on fiber optics for in-well monitoring for phase 2. So if I want to bring a message across is that yes, geophysics is incredibly important for the success of a CCS project because of look at all what we do. And another message that I want to bring across is that if you have the chance of broaden your skills, please do, because chances are that in a CCS project, there is not a lot of money like there is in the oil and gas industry. Therefore, as a geophysicist, you might have to do it all. And there might not be many with you to do it with you. So with that, I'd like to finish. And I don't know if there is time for questions. I don't know if I took too much time, actually.
No, Catalina, that's just perfect. Yeah, as a reminder, questions and discussion will be at the end of this workshop. If you wish to pose some questions while you think of them during the presentation, please put them in the Q&A box. You'll find that button on the bottom of your screen in your Zoom window, and we'll attempt to address those at the very end. So thanks again, Catalina, for a very nice overview of Northern Lights. Due to the time constraints, I'd like to move on to the next presentation, which is entitled The Path to Net Zero Emissions, Vår Energi's Perspective. This talk will be given by Cedric Fayamendi, who's a geophysicist with over 20 years experience in reservoir characterization and monitoring in Schlumberger, ConocoPhillips, and Equinor. And he's made the shift to energy management and R&D and low emission solution engineering and research at Vår Energi. Thank you very much, Cedric. I think we can see your presentation just fine.
Thank you. Thank you for the introduction. And thank you for the invitation to give me a chance to present today. So I have one slide on the general disclaimer about the statement and forward statement, but what I would like to state today is that I will not be talking about geophysics. I will mention subsurface, but I will not go into the geophysics, and I will try to explain why throughout those slides. So what I will talk about today is say a few words about who we are at Vår Energi and discuss sustainability, ESG, net zero, what does that mean? And then present what we do in decarbonization. And I will mention a CCS project we are working with and conclude. So Vår Energi, we are the second operator on the NCS. We are a Norwegian-based company and owned by Eni and Point Resources, company which is administrated by iTech Vision. And in February this year, we became listed on the Oslo Stock Exchange. So we have a headquarters in Sandnes, in Forus, where I'm sitting today. And we have also offices in Hammerfest and Oslo. So we are operating 4 fields on the NCS, Balder, Goliat, Marulk, and Ringhorne. And we are partner on 32 producing fields. So we are a mid-size oil and gas company with 900 employees, and we are producing about 250,000 barrels of oil equivalent per day. So like a lot of E&P companies, we have set some goals for decarbonizing our portfolio. One of our strategies to be a ESG leader. I'll come back to what that means. And we aim to be a net zero emitter from our office building and businesses travel employee commuting by 2021. By 2025, we aim to be net zero from our offshore marine vessels. And by 2030, the objective is to reduce by 50% our scope 1 greenhouse gas emission from our operated assets and net zero from operated assets and equity share of partner operated asset. So a few words before I continue about at least some definition about sustainability. I mentioned ESG, I mentioned scope 1. So a few words of what it means. Maybe most of you knows that already, but the sustainability goals have been built on several years of work by different countries and the United Nations to support the transition towards a more sustainable world. So we have identified some key goals within the oil industry where we can contribute, and that we've done this with the help of this GRI, the Global Reporting Initiative, which helped us to translate these UN nation goals into risk management goals. So you can see on the right side, the ESG goals that we have. So the E stands for environmental, S for social, and G for governance. And as part of this risk under environment, we have defined what we call the GHG, greenhouse gas emission and air emissions. And this is where we are focusing our work when it comes to decarbonization. And reduction of our scope 1, 2, and 3 emissions. Again, it might be familiar for some of you, but I'll just run through that anyway. The definition of the scope 1, 2, and 3. When we talk about the scope 1, it means the direct emission we are control of. So the greenhouse gas emission that are coming from our installation platform or FPSO or producing assets. The scope 2 emissions are the emissions that are coming from the electricity we're buying from shore. And scope 3 are all the other indirect emissions that are part of the value chain. So we have a good control of what we are emitting. So we have good control of our scope 1 and scope 2 emission. We know where we buy the electricity from. But when it comes to scope 3, it's much more difficult to map all the emission generated by the product we are selling, the gas and the oil. So we still have a lot of work to do on mapping those scope 3. So this is how it looks for Vår Energi. So in 2021, we emitted just below 200,000 tons of CO2, scope 1, and that's about just below 9 kilo of CO2 per barrel from our operated asset. And that's quite a high number. And it's mainly due to the fact that we have aging infrastructures platforms. So what do we do about this? We have three main projects to try to reduce those scope 1 emissions. The first one is the electrification of Jotun, Jotun is an FPSO, part of the Balder area. And by electrification of Jotun, we will reduce the amount of greenhouse gas, because as you may know, more than 80% of the CO2 emission are generated by gas turbine on the offshore. Offshore. So the other project that we have is the decommissioning of Balder FPU, the production unit. The Balder FPU is very energy demanding, and it's emitting a lot of CO2. And at some point, it might be more economical to stop the production at the Balder FPU than the continuing of producing and paying taxes of CO2. So we are looking at the right timing for decommissioning this field. And the third big project that we have in our portfolio is a project called Barents Blue and Polaris, and I will say a few words about that. Barents Blue and Polaris. The Barents Blue, that's the name of the project, and the project partnership here plans to utilize a reservoir to store some gas, but the Barents Blue project is about producing blue ammonia. It's a project that we have in collaboration with Horisont Energy and Equinor. So the idea with this production of blue ammonia is to use natural gas, process the gas in order to generate ammonia, and throughout this process you need to take out the CO2 in order to generate the ammonia. Polaris is the name of the reservoir where we will store the CO2. So this is a bit more information about that project. So the project will be located in Finnmark, not too far north of Hammerfest. And again, the idea is to use the gas that is produced in the Barents Sea, process it onshore. So throughout the process, we will extract the CO2 from the natural gas, and the CO2 will be transported back offshore into the Polaris reservoir. This is a very early project. We haven't passed DG2 yet. Plan is to have DG2 by end of 2022 or early 2023. And the startup is a bit of uncertainty around that, but around 2027. There will be several phases of the project. So the transport and the storage might increase over time, but we are talking about an injection volume of 2 million tons per year in the first phase. Here we will capture the CO2 and reinject it, but the capture rate will be about 99%. So it's not a 100% carbon removal project. So again, as I say, this is an early phase in the project. So there's a lot of people looking at the reservoir characterization for now. And as it was mentioned earlier, a lot of work is done on the interpretation part and on the reservoir characterization part. There's only one well in the area, so a lot of risk assessment is done on the seismic. So the more we can extract from the seismic, the better we can characterize the reservoir there. Yeah, and that's our main project we have with CCS. So the rest of the the time I have, I would like to maybe reflect on why we don't have more CCS project in our portfolio as a company, but also as an industry on the NCS. And most of the energy company are trying to decarbonize their offshore installation, and it's not that CCS is the best solution in all cases. So here I've just listed 4 possibilities to decarbonize an installation, and one is offsetting. So you can keep business as usual and buy your decarbonization with offset credits, but that's really offsetting the problem. That's not realistic, and it could be very costly in the future. Another solution could be to replace the fuel of the gas turbine with what we call CO2-free fuel, like ammonia or hydrogen. And there's a lot of work, there's a lot of research done in that field, but it's still low technology level. So it's a technology that's not very matured yet, and we are lacking a market for ammonia and hydrogen. This is not a fuel that is easily available. It's quite expensive for now. The third option is to install the CO2 capture facility at the source, so at the platform, and you could use the captured CO2 and inject that in the reservoir as part of EOR project to improve the drainage. Or you could inject that captured CO2 in a separate reservoir. The challenge with this is that it's a very high capex. We are talking about capturing small volumes of CO2. And if you think about installing a capture facility with potentially some CO2 processing capabilities that you need before injection in an existing platform, and you need to drill a well to inject that CO2, it's very costly. So the business value for that is very low for now, and I'm not mentioning all the technical challenges with the footprint. It's difficult to have the aerial available on the platform. It's adding a lot of weight as well on the platform. So there's a lot of technical limitation to that. And the fourth possibility is electrification. That's most of what most of the E&P companies are doing those days. They are electrifying their fields. So you can get power from shore, or you can use what we call power hub or small wind farm, like what is done on TempNet, for instance, where wind farm will provide electricity to Gullfaks and Snorre. You can have also power hubs, and you have several ways to define a power hub. On Johan Sverdrup, on phase 2, it's considered like a power hub because Sverdrup will also feed other fields like Edvard Grieg with power. But Sverdrup gets power from shore. You can have a power hub, autonomous platform, getting gas from different fields, providing electricity with a gas turbine, and capturing the CO2 from that gas turbine and storing it into a reservoir. So different ways to look at that, but those solutions are not very mature yet, and they need a lot of collaboration. Those points here illustrate a bit why maybe we don't have more CCS project as an energy company. Working on CCS alone is very challenging, and this is illustrated as well with this graph here that I slightly modified after a report from DNV on the cost reduction from CCS. You see on the y-axis, there's a cost of CO2 in NOK per ton, On the y-axis, on the x-axis is the volumes and the timeline. And the blue curve here is the cost from investor perspective, and the green from the Norwegian Environment Agency. But you can see that, for instance, I've put the Northern Light project here, at least the phase 1. They're looking at a very high cost for CO2. And when you think that the EU ETS cost today is about 800 NOK or 850 NOK, about 80 euro per ton, you can see we are far from getting value out of that project. Of course, but when they will get access to more volumes, then it will be a time as well where hopefully the CO2 price will increase, and then maybe the project will see more economy. By 2030, the Norwegian government had an ambition to put the cost of the CO2 price of about 2,000 NOK per ton, and yeah, depending on the speed and depending on the behavior of that cost, the CO2 cost curve, I don't think we will see economy into the CCS project before 2025. In addition to that, it's the type of project where you require a lot of collaboration if you want to look at the total value chain. So it's difficult for a mid-size operator to go there alone. So to summarize, I would say that our company, but I guess it's the same for a lot of mid-size operator, we are committed to decarbonize our portfolio. And we're not just looking at the scope 1 and 2. There comes a lot of new regulation now from Europe, where we have also to report our scope 3 emission, and we will have to address and to maybe decarbonize our scope 3 in the future. But for today, the main project that we are working with are electrification, decommissioning, and a lot of work is done as well on energy management to look at the complete picture of how energy is managed. We're also supporting a lot of research projects. I can mention the Low Emission Center with SINTEF. There's an NCCS project with SINTEF, and we're also supporting a new project with Aker Solutions called Lean CCS to accelerate the transition to CCS and reduce the cost. The CCS projects are still challenging from an economical perspective, so we need to reduce the cost. So that's an obvious action, but we also need to scale up and work on the standardization. And to make those projects successful, we are also to collaborate and secure access to volume. But as Katarina alluded that earlier, we have a lot of competence in place. We have a unique position there because we have competence from subsurface, from the production side, the processing of gas that we can use. Transport to some degree, but we also have a good knowledge of how to market our product. And all those competence can easily be transferable to CCS. So we are still working in Vår Energi to look at opportunities and how we can concretize and be more proactive in that domain. But there's still a lot of challenges ahead of us. That was my last slide. Thank you.
Thank you very much, Cedric. Very interesting overview. I'll pass quickly in view of time to our next presentation. I'd like to invite Dr. KM Stræk, who's the president of KMS Technologies, to talk to us about verifying CSEM measurements for CO2 monitoring, a case history. His company has quite a history in doing borehole and borehole surface, land and marine electromagnetics, and linking it with 3D seismic earth models to get answers from the subsurface. Oh dear. Well, I'll leave you to it. Take it away, Kurt. not there yet, but yep, now it is. Thank you, Kay.
Okay, because I have two here and I need to give you the right one. Okay, well, good morning, everyone, and thank you for having me here. And it was quite interesting to listen to the first two presentations. So I will not show you a disclaimer slide. I show you a claimer slide. So this equipment really works. And we guarantee it for a long period of time because we cannot afford having it shipped back. But this presentation is exactly the opposite from a disclaimer. I am trying to show you that we can guarantee our measurements and measurement results from the baseline measurements within the accuracy of the borehole logs. So we can say from the measurements after we have them, and whatever we do with them, which of course is all transparent, that it is correct within the accuracy of the log. So hopefully I get this point across. And let me just start with the presentation. So when we started this, we asked ourselves, if you want to monitor CO2, what the heck do you do? And from what I heard today, I don't think the geophysicists know what we do yet. And I don't think I know what we do, but I understand a little bit about electromagnetics, what we do, and not much more than what I show you here today. Even though it may look that way, it's not true. Now, what geophysical methods we select, and this is not only among the different geophysical methods, also within electromagnetics, there is a lot more than CSEM. And within CSEM, there is even 10 times as many CSEM methods than there is among the other electromagnetic methods. So you can choose many methods, and the difference in seeing or not seeing something can be as much as 100 times clear or unclear. So I'll give you one example, a well-known example, and I'll support that with some data, and I leave out those examples that I used to show at meetings, that because I don't have the hard data to support those claims that our community has made over the past 10, 15 years, maybe later when we get the data. And I also give you an idea how we translate all of those requirements into field operations. We carried out about a year ago, a little bit more than a year ago, a very large baseline survey over the largest CO2 pilot in North Dakota. And today I only talk a little bit about the plan and feasibility, but I will talk more about the results and how these things link together, so that you can judge it. So some of you that may have heard a prior part of this presentation, what you will hear different today is that everything that is in those presentations that are out there has actually been confirmed. How do we see an electromagnetic anomaly? And what are we looking for when we monitor CO2 plumes with electromagnetics? We get the CO2 usually dissolved in brine, and in the northern light, you are injecting in a saline reservoir, and the CO2 can go up to 60% in solution with the brine. And we are trying to figure out how we are going to see this. So electromagnetically, we are trying to see the CO2 saturated brine, which is resistive, and we are also trying to see the brine itself, which is conductive. So we need to measure electric and magnetic fields, and we need to use as transmitter, if we talk CSEM, a grounded dipole. That's gives you the most unbiased resistivity. And that's proven over the last 30 years. So I'm not talking about how and why and so forth. There is still one part of the disagreement, and that is the lateral movement of the CO2 plume inside the reservoir. From our experience of looking at a large number of EOR reservoirs around the world, I feel more comfortable with 100 meters of CO2 plume expansion per year. But our client in North Dakota did numerous reservoir simulator models, and they used all kinds of other geophysics, and they are convinced that the CO2 plume moves 200 meters per year. I think that's very optimistic, but I can't ignore it. So that's what we have here. Now we need to see the CO2 plume in the presence of the overburden. And for our purposes, the difficulty is that all of the important storage reservoirs are deeper than 1,500 meter steps. The one you're talking about is 2.7 kilometers, which is fine. And that means you have to use high power transmitter. It also means that surface measurements alone will not be sufficient. So you better plan from day one to go in the borehole in order to see the anomaly. And this is probably true for most geophysical methods, for sure for gravity. Without borehole gravity, it's going to be excessively difficult to see a CO2 plume moving. Now for resistivity, to give you the summary, there is usually an expected change of resistivity between 60 to 50 times. And of course, when you just take brine versus clean water, there's another factor of 10 in there. So you have to make sure that you include the large variety of the mixing components. And if you do this correctly within the context of petrophysical model, you actually get up with quite some strong anomalies. So there are two parts that geophysics is looking for. One, and this was mentioned before, is the reservoir seal. And for that, you obviously use microseismic, which is best. And the reservoir seal is shown below here. It goes along the grain-to-grain contact. And when it breaks, you get a microseismic signal. Now, we have been observing, and we make electromagnetic instruments for all applications, for all geoscientific applications and space applications, as well as military applications. So we see a lot of times earthquakes with EM signals, and they always come before the microseismic signal, because before this reservoir seal here, do you see my pointer?
Yes, we
Yes.
do.
Okay, I'll go to a laser pointer too. So before this seal breaks, you impress forces on the pore space, which has fluids in it. And the minute you impress forces on fluids in reservoir pores, the fluid gets mobile. When fluid gets mobile, the water included in those fluids, which are usually polarized as you see above, plus and minus, they will connect, the electrons flow and the resistivity reduction occurs. So you always get a dramatic resistivity reduction for any mobility in fluid in pore space. I'm not going to talk about that in this presentation, because I'm still looking for more case histories in the solid application. I will talk a little bit and show you an example about CO2. And so when you inject the CO2 combines with the mortar and builds larger molecules that are neutrally charged. They simply block the electron flow, and these are the water molecules. And so CO2 injected brine is the same as the brine. So I really need to see some lab measurements to see some density variations in there. And so then you get a dramatic resistivity increase if you inject CO2. You can imagine that CO2 can go up to over 60% in solution in brine, 60% of the fluid volume. So you will have a really strong resistivity increase. On the right side is some data examples where we recorded from some monitoring experiments the electromagnetic components, electric and magnetic field, and 3-component geophones. It's just an example. Now, what do? We start out with the feasibility, and was very pleased to see in the first talk about the large effort that went into the seismic experiments, because nobody ever wants to pay for 3D feasibility for any type of acquisition. And based on that feasibility, we design a survey, the data gets processed, and then what we now are adding is a predictive optimization where we enhance the anomaly because we realize the anomalies can be small. And we have the capability by modifying the CSEM method and the processing and also using various types of borehole sensors to increase the anomaly by combined up to a factor of about 100. The methodology about 10 to 50 and the borehole sensors about 5 to 10. So combined, I'm saying about 100. And then when this is done, you can go routinely in time-lapse measurements, and they will be always the same. This is just acquiring the data. Let me get this. No, I have a nasty window on my screen. You may not see that one from Zoom. So I've said this, CO2 saturated brine is resistive, but we also need to map the conductive part because we also need to see where the conductive part retreats. I'm looking at two methods in this presentation. One is magnetotellurics. Magnetotellurics is based on electromagnetic waves going into the Earth. This is in the very northern part of the globe. And then as you go lower, you get a decrease in frequency. The Earth is a low pass filter. And then you get a response back from the reservoir. You measure electric and magnetic field. And from that, you get an idea about the resistivity. The resistivity should also always be a tensor resistivity. That means you need to have directional measurements. And the Earth should always be anisotropic. I won't emphasize that more in this presentation. Let me just say that the error by not doing it is at least 40%. So when I say the error is 40 to 50%, I'm trying to be polite. So you need to consider everything being anisotropic and directional sensitive. What we do is we inject the square wave, and you saw this here with increasing time, the signal goes outwards and downwards. Here, the current flows perpendicular to the screen. And then we measure with a number of arrays. These green dots are shallow boreholes, and these are shallow borehole receivers. They have 3-component magnetometers in it and 3-component geophones. And on the outside of the casing for these boreholes, we put electric field sensors at the surface. This is a transmitter, which is a 150 kilowatt transmitter. And this is the receiver next to a power plant in our survey. And this box we use to ship the data directly to the cloud so that when we acquire the data in North Dakota, we can process it in Sweden or in Germany and in the morning tell the guys in North Dakota, do this, do that. On the left side, we have a reservoir when you use magnetotellurics. And I apologize, this is not covering up strong enough the picture in the background. And on the right side is CSEM. So when you use magnetotellurics, a passive method, which would be comparable to microseismic versus active seismic, then you get an image like this. And this is very good in interpretation. And I'm really amazed how well magnetotellurics and audio magnetotellurics works these days. It's made tremendous progress. But CSEM can be better and can give you a better picture than this. But clearly the state of the industry and the state of interpretation for CSEM is not as advanced as for magnetotellurics. And you can see that in the data. This is the data from North Dakota, the magnetotelluric data right on the parking lot of the power plant you saw is the red curve, is a high noise area. This is the MT data in a low noise area, and the CSEM data is just simply stronger. And in the high noise area, it is lower. For those of you who know something about electromagnetics, this is because there is a huge amount of noise riding over the signal, so automatically our amplifiers go down in gain, and that's why this signal is much smaller. And when you average the signal, you still get the signal, but the noise disappears. But if you put them raw on top of each other, you will just see noise. Now, what is happening when you inject? Then after you get a signal as a baseline measurement, and that's what I'll talk about now. And the biggest question is, how do you tell the client you're going to see something in a time lapse that they have to spend money for it? So that's what I'm trying to answer in this presentation. Then a few years later, you do measurements, you see some changes, and then another few years later, you see some more changes. It is not always years. It is not always years. It could also be days. We have some EOR examples where we saw a water flood at 2 kilometer steps within 2 days. But years in a CO2 case is normal. In our case in North Dakota, at this stage, we say that the repeat time between measurements should be between 12 to 18 months. And we derived this from 3D modeling, where we essentially build a 3D anisotropic model. This is the injection site in the power plant you saw. And on the right side are the composite logs. We built an equivalent log, an anisotropic log from these composite logs. These are these blocky curves. And the response from these logs are identical to the very fine log. That's why we call it equivalent log. And we then calibrate everything against this anisotropic log. So this is the most important part. The petrophysics and the fluid substitution, and doing that correctly and estimating that correctly is the most important part. So I would not recommend to do electromagnetics unless you have borehole control. You can do it as a risk, but I would be very careful. And the measurements we carried out used 4 transmitters, one cross dipole transmitter to the north, one to the south, and we made 3 lines in order to save money instead of complete aerial coverage. This is the planned injection site. We put the lines at this place because there are additional wells here and potential future injection sites. And so that's why the survey area looks like this. Every 600 meters is a magnetotelluric station. Every 200 meters, a complete CSEM station with 5 to 8 components from 4 dipoles. So we ended up with about 150 or 130, well, you'd see it later, individual sites, but a total of 3,500 inversion pairs. The target itself is in the Williston Basin in North Dakota, and the 2 injection targets are the Broom Creek at 1,500 meters and the Deadwood at about 3,300 meter steps. This is a projection of the survey area on this geologic cross-section of North Dakota. The planned injection is 4 million metric tons per year. I don't know when they start injecting, but within the next year or year and a half, they will start their injection program. So let's go on. And I've already talked about the fluid substitution, so I can save those. One key element is not only the fluid substitution, but also the noise we measure in the field. So we go with a large number of sensors. Since we manufacture all of our equipment, including the sensors, we take various sensors with us to the field to test the noise levels. And here we have the different noise spectra for the different sensors. And then on the right side, we have essentially 3D anisotropic models for the model derived from the log you saw before for various offsets. And these are the power spectra we measure in the field beforehand. And we are setting up the survey so that the response curve with or without injected CO2 is above this noise, so that we can actually run production and carry out a survey by a seismic-coup. There was not a single geophysicist in the field when this data was acquired. There was one in the hotel doing QC, a junior geophysicist. The other ones were located thousands of kilometers and continents away. From the 3D modeling, I'll show you some examples here, where essentially we have different responses, and you will see them in a minute in 3D, but the 3D plots are really boring because you can't see anything. They just look pretty, and my mouse disappeared. There we go. And what we have here is essentially at the bottom, the percentage anomaly. At the top, we have absolute values, what we measure, voltages we measure. And the noise level is drawn right here. And here we have the 150 meter radius plume at the injection site and 100 meter spacings between receivers. Here it's 200 meters, and on the right side is 300 meters. So what do we use these plots for? These plots are very similar. So they behave the same, the curves are right in sequence, and you can essentially interpolate them. So what this says, if you would do 100-meter measurements, you are heavily oversampled. 300 meters is acceptable. By the way, the 400-meter plot is not thrown because the curves start crossing. And you realize that 400 meters is undersampling the anomaly. And so we selected a 200-meter, the CSEM spacing, which is quite important for acquisition time and processes. And here we're talking 24-hour acquisition time at -20-degree outside temperatures, which requires 2 complete field crews. And it's not an easy undertaking. So here are the 3D plots. The blue one is the noise, and you can see one of the components here, the EX component is above the noise. The black one, here it's only partially above the noise, and the magnetic field is below the noise. The magnetic field is always smaller than the electric field, so it's more hard to measure. And this is the radius of 500 meters for the plume, and here the radius is 100 meters. Now, I'm showing these because the anomaly with a small radius is very, very, very small. So for sure, we have to do a lot to enhance this anomaly, because this anomaly is really too small to determine. From our calibrations at the beginning, at the end of the survey, we determined that the worst repeatability, so the worst we can guarantee our measurements, is between 0.5%. We were better than 0.1% in most receivers and for most transmitters, but 1 or 2 were around 0.5%. So obviously, we have to go with our data. Our repeatability is better than 0.5%. And so measuring an anomaly that is this small is challenging. So the result was the Inyankara is very shallow, so I won't talk about it. We can see the Broom Creek and the Deadwood at 3.3. We would have to do some focusing in order to see this. Here's some results from the survey, and I go through it a little bit quicker so you can see a little bit more about the real data. We selected this section for the display here of line number 1. And I don't know which transmitter we use, whether we use this transmitter 1 or transmitter 2. It doesn't matter. They gave the same results, except from this transmitter, the signals were a little bit cleaner from the second one because we got twice as much power in. We used a 180 kilowatt generator, about 250 amps. This is the transmitter. These are the electrode pits. These are the layout for the MT sites and for the CSEM sites. And we had 42 MT sites, 125 CSEM sites, which gave us about 3,500 independent inversions. There's a lot of redundancy built in for various purposes because we already acquired the data that we can later on apply some data focusing techniques and enhance the anomaly by a factor of 10. 24-hour operations. The equipment worked for 2.5 months or 3 months without any breakdown at -20 degrees C. And the maximum deployment was 24 layouts for the receivers and 16 full to 17 full recorded site per days. And that does include repeats. So the repeats were controlled from either the quality control guys in Germany, Sweden, and in Houston. And the guys in the field would just operate the data. And this is how beautiful it is, but it is freezing cold. Now, the data is sent directly from the transmitter and the receiver to the cloud into the data layer, and then there are several other layers for other purposes. And the quality assurance is absolutely essential. So one guy, 24 hours a day, is making sure that all of the data is correct. And this is at the transmitter side, and once in a while when the equipment gets brought in, it gets verified and calibrated. Here is some data from the magnetotellurics, and on the right side are some 3D inversions, and this is essentially the result you get within 7 to 10 hours. This is the single site where you measure the data. The data has this hump in it, and this is the model which matches the borehole log. So the 1D inversion is essentially the borehole log in black that I showed you before. In this case, the horizontal resistivity, and the red is the inversion result. And when it was like this, and these are unsupervised inversions, so there's no fine tuning. Any geophysicist can match that perfectly. We are happy with it. But we still have this here. So then we used a remote reference site about 300 miles away in Grand Forks, North Dakota, at the university, and apply this remote reference to reduce the noise. And you can see it gets much better. And then within 1 week or so after the MT was completed, we produced these 3D inversion results.
Can I ask you to move to conclusions?
Data,
we're running out of time.
This is the data, and I told you before, the noise is overwhelming, but after it's averaged, it automatically gets like this. The important part is that there's very, very little filtering being done. The data is so high quality that this is essentially just averaging the raw data. Now, how do we quality control the data? We compare it continuously to the 3D anisotropic log. And if the inversion is far off, then we have some problems with local minima or whatever. It's not the starting model because we barely give it a starting model. And then we look at the eigenvalues of the inversion, and we need to make sure that our parameters are set such that the eigenvalues are randomly distributed from the lowest to the deepest part of the layers. So not that we are resolving the top and not the bottom and so forth. So that's really the key element in the inversion parameter workflow setup. Here is again a comparison with the MT results. This is a 2D inversion of the MT, and this is also line 1 and 1.5 kilometers of adjacent sites for the CSEM. And you can see here, this is the Broom Creek at 1,600 meters, and this is the Deadwood at 3.3 kilometers in the CSEM. And if you put this on top of here, you can see that the MT sees something and sees pretty much the same thing here and something around here, but it doesn't see it as well as the CSEM. And that's just the point I wanted to make. On the right side, we compare this with a 3D model from the log. So the dashed black curve is a response from the logs, the 3D anisotropic log, horizontal and vertical resistivities. The first set is the, on my side, the zoom window is above. So I would assume the first set is the electric field in X direction, and the second one is Y. This means X is inline or cross line. And they all match. And this is the window where the reservoir response is. So the response for the 1,600 meters to 3.3 kilometers would be in this range. So we're only looking at this part. And the match is amazing. So if we get a response like this, we can pretty much confirm that our measurements are correct and all of our calibrations are correct. And at the end, when our client submitted this to the SCG, I asked him to just put a seismic section behind. We didn't have it, and he did. And I cut this out of the PDF file. And this is the seismic section. And these are, again, the reservoirs. And it matches amazingly. So we were very pleased with this. And again, I've said many times what the conclusion is. You need high power. You need to measure multi-components. And you need to be able to adopt your array to the anomaly you're actually trying to map. And it's very important that you use real-time quality assurance. Without that, the data quality would not be as high as this. And of course, you need to add the borehole. One of the things we learned from here while we're verifying the baseline data is that repeat service need to include focusing and shallow borehole sensors to make sure that we get a 10 times larger anomaly, at least, if not even more, before. And so I think this is the last slide, unless you want to see equipment. So thank you for your attention.
Thank you very much, Kurt. We're running a bit behind schedule, about 15 minutes. I think everybody would very much appreciate a 10-minute break still, since we've been through our 3 presentations so far. So if I may, I'd suggest we take that 10-minute break and come back at 13:35 in 10 minutes. Where Fiona Sutherland will introduce the next talk. Thanks for being patient with us, John. We'll see you in about 10 minutes. Thanks again to all the speakers, and a reminder once more, if you have any questions you'd like to ask in the discussion, please put them in the Q&A window, not the discussion window. Thank you very much. Well, welcome back, everybody. I hope you had time enough to have a short break. I'd like to start the second half of this session with a presentation entitled 4D Gravity and Subsidence Monitoring for Offshore CO2 Storage, given by John Evan. John Evan is responsible for business development at Octio Gravitude, and he loves to talk about new technologies, and looking forward to seeing what's in his presentation. If you'd like to share your presentation, John, and I leave it over to you.
Okay, fantastic. Then I'll start. I'm going to give you a short introduction about the 4D gravity and seafloor deformation technology, and also talk a little bit how this can be and how it actually is used for CCS monitoring. Just a couple of introductory slides here. I mean, we are all familiar with Newton's law of gravity that we learned in school, usually related to basically calculating how objects in the universe are attracted to each other. The law is very simple. It's stating that there's an attraction force between masses that depends on the masses, the magnitude of the masses themselves, and also the distance between them. And this is actually a principle that we have used in the oil and gas industry the last 20 years to basically understand how typically gas reservoirs are being depleted with time, and basically have the opportunity to see water entering into the system. The way this technology is used for offshore purposes is with the instrumentation pack that is mounted to a ROV. So it's basically a small vessel. You go out to the field, you mount this small piece of equipment to the ROV. This is a standard work class ROV. Inside this center frame, we have 3 relative gravimeters and also 3 pressure sensors. The way we are acquiring a survey is that we are going around on the field and performing measurements on concrete platforms distributed over the fields, like these white circles you can see. And these concrete platforms, they are completely passive elements that you are placing at the field one time, and just before you start monitoring, and then you are basically picking them up after your monitoring campaign is finished. That can be after 20 years, 50 years, or basically what you defined in your project. I can maybe also say that these concrete platforms, they are something like a bit over a meter in diameter, so fairly small ones, and they are about half a meter tall. So small elements, you place them at the seabed, so we have a stable place for repeating our measurements. I also wanted to give a bit of an overview what this looks like. So not necessarily how it would look like for CO2 storage, but this is the giant Ormen Lange field, big gas field in Norway. And here you can see all the concrete platforms distributed over the Ormen Lange field. You can see that if you count them, it's about 120 of these platforms. Most of them are located inside the rim of the reservoir itself, but there's also some measurements taken outside. And the reason why we have some measurements outside is because we want to capture tiny differences in the water column that may be different from survey to survey. So this way we are able to capture the differences in the water column, and also in order to capture tiny differences in the drift of the 2 surveys. I think I also want to mention that when we are actually doing a survey, we are also populating the area with tide sensors. This is a way for us to actually capture the magnitude of the tides and also correct that when we are doing the processing of the data. What we will get when we are acquiring this data is basically two independent measurements. One of them is of course gravity, which is sensitive to mass change, and the other one is seafloor deformation, which is actually sensitive to deformation of the reservoir itself. These two data types actually have independent value because they are able to capture different things, like for instance listed in this part here. But I also wanted to mention that it's very important to actually measure these two properties at the very same time, because if we are measuring a gravity response between two surveys and we are actually having an elevation change, so in the case of gas production and we have subsidence, and when we are repeating our measurement, we are actually moving closer to the reservoir due to the subsidence. This will introduce basically a gravity. This will have an effect on gravity. But when we are measuring the seafloor deformation, we can correct the gravity response in such a way that what we are actually seeing on our data is only related to the mass change. So this means that we can use the 4D gravity to map the injection plume and also measure the CO2 density. And if there is cases where we see vertical movement of the CO2, this is actually also something that can be seen on the data. When it comes down to seafloor deformation on its own, it can actually give us some maps of both the stiffness of the reservoir and also how the pressure is distributed. Since this is the technology that is traditionally used for both the CO2 and hydrocarbon, I thought I would just spend a bit of a minute to explain why this technology is used, first of all, for hydrocarbon production, before I talk about CO2, just to put things in a bit of a context. But at the end of the day, what we are looking for here is efficient reservoir management, so where we can better understand the depletion of the field and basically target untapped reserves. So for instance, this simplified example is showing where we are producing from one segment. There's a sealing fault, and the aquifer is only entering and filling up the produced areas from this area on the right-hand side, while there's no changes happening on the left-hand side. So this is actually a scenario where 4D gravity and subsidence monitoring or seafloor deformation monitoring actually will be able to capture what is happening, and this means we can actually target the infill well here. So with this type of monitoring strategy, you can actually have incremental production for a hydrocarbon and also efficient. You can plan your topside infrastructure more efficiently. One example is the ability to actually see water. So this is kind of the most important value proposition for this technology seen from a hydrocarbon point of view. Another element is that this is cost-effective technology, costing only 10% of 4D seismic. And as you saw with this small instrument we have on the ROV, this is much simplified operation and logistics. When we are moving over to CO2 storage, what we are looking at here is the ability to actually constrain the uncertainties in the volumetric expansion of the injection plume, reduce the uncertainties in the CO2 density, and also have a better understanding of the pressure communication in the reservoir. And a very, very important part is also detecting vertical leakage of the CO2 plume. So from a field development point of view, it's all about the ability to optimize the injection rates and also confirm the long-term containment of the CO2 and also the storage capacity. So just wanted to mention both of these because the principle of the technology, what we're able to measure is basically the same, the value proposition is a little bit different for natural reasons, obviously. I also wanted to kind of say something about the sensitivity of this technology, because many of you may be familiar with gravity measurements, which is sometimes taken from airplanes, or in some cases also acquired during seismic surveys. These data types have resolution in the typically in the milligal region. When we are acquiring this type of data at the seabed under stable condition, we are talking about microgal resolution. But also during the last years, when we have developed this technology, we have actually managed to improve the resolution of this technology. And as you can see from this publication we did in 2020 together with Equinor over the Snøhvit field, you can see that over the time periods of monitoring the Snøhvit field, we have a factor of 5 improvement in the uncertainty on gravity, and also an improvement on how we are measuring subsidence. So you can actually see that we have the ability to see changes in seafloor deformation to around about 2 millimeters, and for the gravity changes we can see, and I think this goes for the last 4 years, we have had average uncertainty in for the gravity around about 0.66 microgal. As you saw from the presentation from Northern Lights earlier, they stated that the technology had a resolution of 1.2 microgal, and I have to just comment on that, because when you are measuring gravity, you always have to correct for subsidence. So if there is some specific care you need to take with regard to oceanography and so forth, this resolution here may go down. So we usually state that the 4D sensitivity is around about 1 microgal, although the measurement we are getting have a higher sensitivity, but it's been drawn down by the effect of the seafloor deformation. Also wanted to say a couple of words about the track record, because for many people this technology is actually quite new, but it is a technology that has been used for over 20 years. It was developed inside Statoil and Equinor in the late 90s, and we have worked with this technology in OCTIO since 2013. And you can see we have quite a bit of experience on our side, and the main applications we're doing this for is the big gas fields in Norway, in addition to also doing monitoring over the CO2, or the fields where CO2 is being injected. Although it has to be said for the Snøhvit, the main business case for the time being is actually measuring the production and water breakthrough. At the end, I just wanted to show you a bit of a field case just to get the feel for how does it work and what is the data looking like. So I'm going to show a case that we again published in 2020 with Equinor from Snøhvit and Albatross. It's a field located in the Barents Sea, water depth around about 300 meters. In the reservoir, we have gas, condensate, and oil. And the Snøhvit field, which is the one I'm going to focus most on here, is located about 2.3 kilometers below sea level. It's a horse block bounded by large faults. So that means that there's actually limited possibility for lateral water movement in this area here. production is taking place by pressure depletion with 7 production wells at Snøhvit. So what we are seeing in this picture here is actually a map over the subsidence between 2011 and 2019. And here you can see this is a typical 4D data set coming out of this technology, where all these numbers are basically measurement numbers, so measurement number 1 and 37 and so forth. You can see that the size of these circles are referring to the amount of subsidence. In this case, you can see that the bigger ones here have around about 1 centimeter of subsidence over the 8 years of production on the field. And what we're using this data for is in this case actually trying to compare the observations with the expected compaction in the reservoir model. And this directly gives insights to the pore volume compressibility in this case. So here we were actually able to significantly reduce the uncertainty in the pore volume compressibility. And you can see that we were almost able to reduce it with a factor of 10, since the uncertainty was between 1 and 8 times 10 to the minus 5th bar inverse. For those of you who are familiar with these values, this is quite low compressibility, but this is related to the fact that the area we are in the world is an area that has been exposed to quite significant regional uplift. So that means that the Snøhvit reservoir was actually buried about 1 kilometer deeper than what is the case at the moment. At the same time, I just wanted to mention the gravity change on Snøhvit and Albatross. And here we can see, again, here, this time we see 2 colors. We see a blue color for the case of increase in gravity, and we see a red color related to decrease in gravity. And it is at the same time, we are interpreting the decrease in gravity as an effect of production. So we're taking out gas from the reservoir itself, and the blue is actually water coming in. So we remember the large faults bounding the Snøhvit structure, and what we're seeing here is actually water entering in, most likely from below. And by the way, also here you can see that the sizes of the circle here is again referred to 5 microgal. So 5 microgal is this one here. So you can see the biggest ones here are actually a little bit bigger than 5 microgal. Just a fun example, here we are seeing an increase in gravity in this area here, which is a bit interesting because there existed faults in this region here, and observing that we actually have a positive change in gravity is indicating that this segment has actually been produced and water has entered into the system. From a history matching point of view, what is also being done is that all these different points with gravity changes can be used into the history matching process, and you can actually quantify the aquifer influx and also try to give a better match with your reservoir model where you are implementing your water influx. Yeah. So it's an improvement compared to just trying to match the reservoir model with the bottom hole pressure of the wells. So that was basically the story I wanted to tell. So I hope I have shown a bit about how this technology can be used for efficient reservoir management of these CO2 injection storages. Constraining uncertainties in volumes and also CO2 density is quite important points for this technology, and also detecting vertical leakage, leading to optimizing injection rates and long-term containment. But finally, I think I want to to mention, I think one of the best things about this technology is that it is quite easy to set the expectation. You could see from Northern Lights, they have done a forward modeling exercise, seeing that you need a certain amount of CO2 injection before you are able to see a signal. And since all we are talking about here is Newton's law of gravity, it's actually a quite simple exercise. So if you have a specific field where you are considering for the gravity for your monitoring strategy, it's not a very complex exercise needed to calculate what will be the expected magnitudes. So with that, I would like to say thank you for your attention. I'm looking forward to the discussion afterwards.
Thanks a lot, John. That was a really interesting talk. Sorry, just turn my video on. Yes, really interesting talk there. Really nice case studies. It's really nice to see how gravity is just seems to just be improving and improving in quality. So our next talk continues on the monitoring strategies, and it's Sven Ellingsrud, which I really hope I pronounced your name not too poorly, talking about can 4D CSEM be a monitoring solution for offshore CO2 storage sites? Thank you very much.
Okay, so I will go directly to the contents there. So first, there is a little bit of introduction and motivation for looking at CSEM and CCS. I will also go a little bit into the CSEM principles. Also, we have heard a little bit from Kurt Stracker earlier today from land CSEM, and I will also go into the principles of what we do offshore. Then again, CSEM for CO2 monitoring and why we think we can see CO2 and how to monitor it. We also got a good introduction there from Kurt. And then again, a little bit into Altan for technical developments and also in safety and acquisition, because it's a lot of places coming up now where the companies want to store CO2. That also might need some precaution on how you use different technologies. Okay. So I'm just trying to okay, so introduction and motivation. So the remote monitoring is, of course, essential to actually observe how CO2 is behaving during and after injection, and also all authorities in injecting it, and then they also want to secure solutions by laws and also when they look at the environmental impact. What is actually important here is to actually address leakages, and also, of course, monitoring the plume and see how that grows and potentially moves and migrate. And also, it's a verification of the stored volume, that nothing is leaks out. Of course, when you inject it, you know how much you inject, but you also want to ensure that the plume keeps the same volume, and so you have control over that. Electrical resistivity is well known to respond to changing fluid type and saturation, and if we can look upon CO2 as a fluid type when it is injected as gases, then it will react to resistivity, and also the saturation gives resistivity. So according to Archie's law, resistivity increases with higher saturation. So if it behaves the same way as natural gas, it is possible to actually detect by CSEM. Also, CSEM allows for delineation and saturation estimates through resistivity imaging. And then again, inversion to image this we use inversion. Okay, I don't know why this jumped now, but if you look at the picture to the right there are some circles. We have Northern Light, that is a circle up in the north where we actually are doing to inject CO2 now. It's also the Sleipner field where it has been injected. And you also see the other small open circles where there are plans or ideas to inject it. So it's popping up a lot of places. Okay, CSEM principles. So when we go offshore, if you look at the two figures on the right side it's basically two different ways to acquire CSEM. Both of them use receivers that you drop to the floor. One is using vertical antennas, the other is using horizontal antennas, and then magnetic antennas. When you use the horizontal method, you tower source, and then you get this energy going into the seafloor, and you detect them by the receivers on the seafloor. With the vertical one, then you have a vertical source below a vessel. It's stationary. You transmit energy, and you are then stacking and detect energy on the receivers when you're doing stacking. When you have finished the stacking, you move to the next position. CSEM is well known also offshore. It's been used since 2002. It was the very first time it was used for hydrocon exploration, so it's a well-known technology. And also now the technology is actually developed. We have some important steps that is important for monitoring, and that is accuracy and also navigation. So the equipment is much more accurate, it's much more stable, and it's also much better navigation, which is important factors when you want to actually do repetitive investigations. And Alton is now in process of developing a 4D EM solution. And of course, if you can use that for monitoring gas production or oil production, it is also under the right conditions. We can provide this for CO2 saturation. And then, of course, if you have the sensitivity. When injecting CO2, it's actually the opposite. You are starting to inject, so you have a really small amount in the beginning. When you are producing, then you have a big amount, and you look at it when it's getting less and less. I'll come a little bit back to that when you are injecting here, on how and when we can start to see it. So if you now look at the slide to the left there, then we have some nice curves from Archie's equation when we are going from water and then up to 100% or 90% saturation. It's for different porosities. So the red curve is for lower porosity, and then the blue one is for high porosity. So when we see at the CO2 saturation level, if we go to 20 or 30%, then it starts to increase rather abruptly. So there is a huge change in resistivity due to the saturation. If you now look at the dashed curve, that is for the PV velocity. It's a very, very big change for the first 20%. And after 20%, it's difficult to actually see the difference between 20 and 90%. So what this indicates is that to actually observe that you get CO2 down there is good with seismic. But it's a little bit more difficult to actually tell something about the volume. But then we propose that you can actually use CSEM to actually take over and tell something when the plume is increasing more, to actually look at the volume there. So the important thing is that then again, formation resistivity from CO2 saturation changes can span over orders of magnitude, and that's important. So it's detectable through remote sensing. Okay, so I'll go to the next one. If you now see here at the nice picture on the right side, we have been on the webpage and looked at a model that is made by Petronas. It's a Malian field. There they have made a reservoir model, and the reservoir model is based on saturation. And what they have done is actually to go in and make that saturation map to resistivity. There are very, very few models like that exist for CO2, but it's the same principle. This is oil, but also oil increases resistivity with saturation. So what it shows really is that you can have a pretty nice and detailed map if you do this correctly. So it's beautiful work by Petrobras, but then again, you can imagine that this also could be done for CO2. So then again, my pages are jumping all the time, so I have to be careful. So, geological storage of CO2 has several risks associated, and that is one, failed caprock seal. Can you see that it's leaking? Then you have transmissive faults and degraded or poorly sealed wells. To mitigate those risks, a CSEM program can be aimed at detecting leaks both for vertical and laterally, and to see them in the faults here. We currently have a program with SINTEF and Total to actually try to see if we can look at that in faults. That is one of the aims, at least. And also it can provide the feedback to injection management and verification and control of the CO2 volumes if you can't detect the volumes and based on resistivity. Okay, I'll go to the next one. Now look at the map to the right there. This is a sensitivity of a real model. This synthetic model is based on reservoir models we have got from site. The model itself is confidential, but the results on the right. It's a deep model, it's a deep reservoir, and we look at now gas saturation, it's increased in the order of 60%, let's say from 20 to 80%. And it's a model here with a conventional toad source. So it's actually horizontal and inline. So the different colors there are looking at different frequencies. And if you now look at the green and the red, that is around 1 Hertz. And then we see at the sensitivity that we have a sensitivity of 10. And we have used the standard sensitivity modeling. It's the equation up there. It's baseline minus the next measurement. And then we look on that on the traditional error bars. Then again, we see that we have sensitivity for this model. Unfortunately, I cannot show the reservoir model itself. At least we see we have sensitivity for that. The modeling suggests that the CSEM have sufficient sensitivity for imaging of saturation changes for this model. What is important and key challenges is that, of course, the resolution of CSEM it's inherently low, and detailed imaging at the reservoir level needs to be addressed through optimization of acquisition configuration. Of course, you need also to have good inversion and improved inversion and accuracy and methodology, and of course also extremely important with navigation, because if you have wrong navigation, that gives you errors. It's also very important to actually do correct modeling, because if it's too deep, if it's 3 kilometers or deeper, you need to do the modeling to see if you have any sensitivity at all. Also repeatability, it's important here. High degree operational accuracy and navigation, as I said, that is necessary to actually get a good 4D signature in the data. And also when you are using inversion, if you repeat 3D inversion, it's also important to actually know exactly how you do that inversion to actually not introduce errors in the imaging itself. One thing that is important for CSEM is infrastructure, that you have proper handling. The pipeline is metal, and if you have a source there that is sending out an electric, you will always induce a secondary source in the pipeline. So you need to be aware on how actually you position the source compared to the pipeline. And also maybe introduce some modeling of pipelines or infrastructure in your 4D inversion program. So it's important to actually take care of the infrastructure. And then again, the sensitivity is based on local geology and rock physics. And that has to provide sufficient resistivity. One thing good when you are doing monitoring is that, of course, you know the reservoir very well from wells and also seismic. You know the cap rock, you know the top of the reservoir, you also know where you have the contact normally when you did probably produce in old times. So it's a very well-known thing, so we can also do this as constraints in your inversion. Okay, so then a little bit about Alton and the equipment. At the moment, we have developed prototypes of receivers. You can see that on the upper left panel. Then you have a receiver with horizontal electric dipoles. You also have magnetic coils, horizontal, and you also have the ability to add a vertical sensor on the top there. Those are now been testing in June here. So they are currently been testing for see if we have to do some minor adjustments. At the moment, we are also having an OBN. You see that little yellow box here. We put it under just to check out if the OBN and the logger in the electric field here are actually affected. If the OBN is creating noise that we measure with extremely sensitive coils antennas, or if we are actually interfering with the OBN. If we find some solution there that they do not interfere, there are some potential also in reservoir monitoring also for detection of CO2. The source will be in different modes. We will make a source that has a streamer antenna, traditional CSEM antenna here, you can throw it. We will also enable it to put it on the seafloor, so it's stationary, both horizontally and also under the vessel vertically. What is an advantage if you add it on the seafloor is that you can stack for a long time and then you get more energy down to the reservoir, actually to get a better picture when you are doing inversion. On the right side here, we have some pictures of our new inversion. We have a 2.5D inversion at the moment and a full 3D modeling. We also have a 3D inversion, but we need to make that for bigger data sets. So we are now parallelizing that, and that is ready for full inversion in Q3. Or no, sorry, Q1 next year. That's the correct data. So okay, we have the equipment here, and also what is important here, we are adding in sensors to get accurate position and also rotation angles to be able to come up with the accuracy that is needed for monitoring. Safe acquisition solution. We have got some questions from different parts in the North Sea that some companies, they want to evaluate to look at reservoir where you have windmills. If you want to inject here, it's pretty difficult to do that with seismic because the windmills are making noise. So they are fastened to the and they create noise. So it's difficult to listen to seismic because the noise is too high. And it's also difficult to get allowance to tow with a seismic streamer here. Then again, if you have a CSEM, you can go in with the vessel. You can drop down your receiver in a fixed position. And if you then also have a source that you can lay on the seafloor in a fixed position, it might be that that is a solution to actually monitor injection of CO2 if you are in windmill parks. Yes, then I don't have so much more, but it's just to mention that it's little published on the injection of CO2. University in Oslo, they did publish something in Nature. See the reference here? And then they say that there is a potential of using CSEM for the injection of CO2. So this is a good reference. There's also another reference coming up now from Stephen Constable et al. They are looking at CO2 injection under hydrates. It's a little bit different setting, but it's an interesting paper that shows that there are several opportunities for actually injecting CO2. Conclusions. There is a need for cost-efficient monitoring or solutions for CCS. And also, there will be a demand from authorities that you need. Electrical resistivity is directly linked to gas saturation and volume within contained volume. And then again, no, it has been a lot of advances in CSEM technology allows for CO2 monitoring applications aimed at leakage and to do mapping and volume estimations. CSEM acquisition can provide a safe alternative in sensitive areas, for instance, where you have windmills and other installations. Also, when you have infrastructure that no monitoring solution will work perfect there everywhere. It's you know that seismic will struggle with gas. Also, we see that gravimetry have some solutions. Then again, also it's important to find a way to actually use CSEM. Maybe a combination could be a nice approach and on different places here for CO2 projects. So that was the end of it.
Thank you very much for your talk. It was really interesting. So I think if you stop sharing now, and then that gives the next person a chance. So our final talk today is by Habib Al-Khatib from Spotlight, looking at CCS monitoring, focused seismic detection to calibrate dynamic models. So are you able to share your screen?
This is a beautiful picture of my team.
We're on the title slide, yes, on the title slide there.
Okay, excellent. Okay, fair enough. So you can see the screen. Okay, so good afternoon, everyone, and thank you for attending all these interesting presentation. And I hope you are not too bored for now. But before we started, I have a legal warning for some of the geophysicists that will attend this presentation. We will, in this presentation, show geophysics and seismic, but we will not provide images. And I know some geophysicists may seem, let's say, uncomfortable with such an approach. So I hope we will have time to discuss in the Q&A about this. So it has been, let's say, said several times before me, so I will not enter too much into the why we are monitoring CCS, but and I fully subscribe to what has been said. Basically, it's not like oil and gas, but for CCS, you monitoring to avoid the surprises. And this is absolutely key. You want absolutely to avoid surprises because unlike oil and gas, where a surprise could mean bypass oil and extra revenue, for CCS, it's always mean bad surprise. So the question is the existing seismic monitoring technology, where I'm talking here about the full field seismic monitoring technology, enough for monitoring? And we saw that a lot of other techniques are trying to be and to compete with this kind of technology. So basically, if I take the example of Equinor and Sleipner, and sorry for my Norwegian, but my accent in French is better than my Norwegian, you can clearly see that they made one seismic every 2 years in average, which means that between the dynamic model, the model you want to validate, and the actual CO2 plume, you let the model deviate for about 2 years, and then you calibrate it spatially with the 4D seismic. You do it again and again and again, and you ended up into a relevant and proven monitoring technology, especially because seismic is, from a physical point of view, the most accurate method to detect CO2 in much of the cases, thanks to the strong response of CO2. Yet, I will advocate that such solution is not sustainable if you want to answer the monitoring with only full 4D seismic. And for two main reasons, which is cost and footprint, and these are the limiting factor. But the last one is the frequencies of the full 4D seismic, which due to cost and footprint had to be sparse in the time lapse. So every 2 years, every 5 years, or every 3 years. So let's look together why cost and footprint could be a limiting factor. Obviously, and especially offshore, the cost of full 4D seismic, it has been mentioned several times, is approximately 10 times bigger than when the EIA itself recommended at the full monitoring cost per MTPA. So definitely, if you want to use seismic, you need a lighter solution as a normal frequent monitoring tool. But obstruction is something that we are, I think, too much underestimate as let's say, obstruction and barriers. And I do believe that footprint is in fact the #1 factor that will prevent the use of full field seismic 4D in most of the cases. What you can see on the left is the original 3D survey design of a field we are monitoring now for steam injection with PDO. And you see all the seismic sources and the seismic receiver that has been used to perform a full 3D seismic image. If you want to do a full 4D survey in this area, then you need to reposition the same number of sources at the same locations. But as you can see, over 10 years, a lot of new infrastructure had been built, preventing a full field 4D. It is same talking about social acceptance, where you can see the footprint of the massive seismic acquisition that will prevent onshore an acceptance of such a solution used on a regular basis again as the main monitoring technology. It has been just said in the previous talk that offshore, you can have windmills as well, preventing you to have this kind of full field footprint, and same for the mammals in terms of acceptance. So whatever the solution is for monitoring, if you want to demonstrate to the regulator and the local people that your solution is going to be suitable for long-term monitoring, you absolutely need to have a more light and agile solution. Having said that, we developed within Spotlight a solution that could provide such a light and agile solution, but to work, it will capitalize on 3 main criteria of CCS that are different from the oil and gas. One is long-term monitoring. We already talked about that. The second one is fast 4D response. Well, when you talk about seismic and CO2, let's say it's pretty easy to make the job about convincing that, yes, you could detect CO2 first arrival with seismic. And when I was attending the great EAG in Madrid, the annuals, I had the pleasure to see on a VSP a one-day seismic 4D response on a VSP 4D walkaway VSP. So definitely the 4D seismic response of the CO2 is strong and fast. And this is a modeling we performed in the North Sea with Greensand and Wintershall on the Greensand project that we are monitoring. It is so strong that you could enable, on a physical point of view, very frequent monitoring. You can do it once every week, assuming you inject enough, and still have a reliable signal. When I talk about reliable signal, I just show you here some real case example we've performed as a monitoring technology, where you can clearly see here two traces, raw traces, slightly processed but not migrated traces from 2020 and 2022. And just by your eyes, you can see a phase shift here that is happening here in the sliding time shift, showing a 2 millisecond change in a 2-year CO2 injection on a CCUS case in Canada that we published in EAGE Madrid. Having said that, the second main part of and main feature of the CCS is that, unlike oil and gas, where Mother Nature, God, or whoever you want is decided where the oil is, for CCS monitoring, you do decide where you inject. And obviously, you're going to go toward simple reservoir model, either on aquifer, saline aquifer, or on depleted oil and gas field. You will go for the easiest one. As the results, the dynamic model that our friend, the reservoir engineer, are forecasting are much more accurate than what it could be for the oil and gas industry. And one of the main examples is on Sleipner, where in fact the model was pretty right, and they managed to precisely forecast what will happen, how fast will the plume move in the general rules. So with that, the question is, do you always need an image to validate or invalidate your reservoir model? And to this specific question, we propose an alternative solution with focused seismic measurement, precisely located in space and time to validate the reservoir hypothesis. So I don't know if you see the GIF, the animated image here, but it is precisely that we are proposing in between full 4D survey or electromagnetic survey or gravimetry survey, in order to tell the reservoir engineer with frequent and focused monitoring where and when the reservoir is changing. If the model is right, then there is no point about performing a full 4D survey. But if the model is wrong, if the detection are not matching with the model, then with focused seismic monitoring, you can't correct the model. But this is the time where you're going to trigger a full 4D survey in order to validate or invalidate, to correct your model. But you are not surprised because you know something is wrong. And this is really important in my talk for you to understand this point. Then how we do it? Well, we developed over the 5 last year a methodology that is using the existing 3D exploration or 4D when we have data set, not as images to be replicated, but as a travel map of all the wave field within the subsurface that we're going to demigrate in order to, or data mine for the non-geophysicist, in order to extract out of the millions combination, the only best, we call it in French, la crème de la crème, the only best sources and receiver position or receiver antenna, where we can't have a single receiver for noise purposes, to detect a change in a given location. And this image is made from one of our STEAM monitoring paper with ConocoPhillips. With that, we are providing a 100% digital analysis on the existing terabytes of data that cost millions to our clients to propose a greener solution with standard equipment, but just 1,000 times less equipment than what you used to do for full field survey. Something that is so light that it could dodge in between infrastructure and be easy to implement. Yet, as we are lacking for temporal stack, we'll compensate for spatial stack, as we don't have coverage, we'll compensate that with more sweeps and a temporal stack of the energy. So offshore, we are even able to use a smaller source, a much smaller source, like few hundred cubic inch source, which is better for the environment as well, but we'll stack in time the energy to recover a proper signal-to-noise ratio in static location mode. Having said that, I will show you how it could be implemented in CCS monitoring, and I will divide the CCS monitoring in 3 phases. The pilot injection, where you want to validate your original hypothesis, which are very strong and that will drive your whole CCS project. Then the plume monitoring phase, where you inject. And I will not discuss too much about the end of life monitoring, because all of the people present here might not be still, let's say, we will all be retired by that time, and technology will so much evolve that I will not advocate for that in this talk, even though we do have ideas for that. So let's come to the first phase, the pilot injection. So this is pretty much what we are going to do on Greensound project end of this year with INEOS and Wintershall. In fact, they have the injection point, and we're going to design using the existing 3D, and by the way, we are designing that, using the existing 3D and exploration seismic, the optimal sources and receiver in order to detect several spots co-located to the injection points. The acquisition, by the way, will be done by Maxsize. What we're going to do then is to frequently monitor. Offshore, we are advocating for every 2 months in order to detect the first spot that will change, hopefully the injection point, and then the next and the next. Why it is so important? First, because you will have with the 4D effect, the verticality of the layers that will be affected by the plume. But second, by monitoring very frequently with seismic, you will be able in the pilot phase to show the regulator the minimum amount of CO2 you are injecting in order to trigger a seismic 4D response, which is the best calibration ever because it is a real measurement calibration and not a petroelastic model only based. With that, you will have a rapid deployment technology with a detectability threshold that you're going to use for the next leakage and conformance detection. Then, after this first month of injection pilot, you're going to do all your computation, decided if you want to go to the final investment decision, and you're going to monitor the CO2 plume extension. For that, this is pretty much the animated image I showed earlier. You have various spots that are defined by the reservoir engineer to eliminate the P10 and P90 scenario, which are the most unlikely to happen, and to validate the most likely to happen scenario. So it is a kind of interaction with the reservoir engineer to detect spots that are supposed to change and some that are not supposed to change. Then you monitor them, and assuming the monitoring is okay and validating your model, then you can change the source and the receiver location for the next survey. When the data quality are good, mainly offshore, but we also demonstrated it onshore, we can use the existing 3D data as raw baseline for our survey. If not, we have to reacquire the next baseline in each acquisition. What is also interesting to know here is to see that we are not believing such a focused monitoring approach, which will be very frequent to quickly know when something is wrong. We are not believing that to be a one and all solution. We strongly believe into the synergies with electromagnetic, gravimetry, and even microseismic, because after all, the other techniques will give you a kind of broader area, especially gravimetry and CSEM, about where the CO2 is going. And if it's not matching your model, then you can add more spots to precisely understand what is happening in this area before calling the whole cavalry, which is a full 4D seismic. But for microseismic, there is also something else, which is microseismic is a real-time measurement. And what happens if a microseismic event is detected in an area where, according to the model, no CO2 should be? Then the regulator might argue that this is a leakage in your reservoir. But passive seismic and microseismic is not suitable to tell you if it is due to CO2 or to other factors, where active seismic is. So after all, this microseismic area, active area, is just another spot that we could quickly mobilize a small crew to perform our 1 or 2 day ops and detect quickly if this is a threat or not to the reservoir integrity. Having said that, and as a conclusion, and I hope I did not overpass my time, capitalizing on the existing asset, which is $1 million worth value 3D seismic, we are able to provide, and we demonstrated on real data, a focused seismic monitoring solution. Yet, we are providing qualitative information and not quantitative. So this is clearly a limitation, but we are here not to correct the model, but to know when something is wrong. So as a kind of triggering of all the other methodology. The way forward is obviously to find more synergies on the operational model, so smaller source, automation, onshore and offshore, but also find more synergies with the other methodology of microseismic, DAS, walk-away VSP, CSEM, and 4D gravimetry. And last, a stronger integration with the dynamic model is critical here in order to create a reliable alarm system with this frequent monitoring, know anytime, anywhere that the model or the assumption is right, and if not, trigger a full 4D survey. Thank you very much for your attention.
Yes, I guess we are moving into the Q&A session, right? We have several questions, and if we start first from the ones in the Q&A box, there's one Ali Karagül. First question came from him. Thanks for the great workshop. Recently, I read a paper where the authors regarding the CCUS risk assessment are arguing that for a CCUS project, the question that we may need to ask is how could the project fail? Is there relevance? Is more relevant than how can the project be successful, which is more common in the oil and gas exploration context. What's the speakers think on this statement? Ali, maybe we can also unmute you, and if you want to follow up, ask a follow-up question. But we would like to address this question, I guess, to all speakers. And who wants to start, please? Let's start with Katarina, Cedric, Kurt in the beginning of the first session. We would like to. This question is, you can read this question also in the Q&A box.
Yeah, I can try to address that question. I think what I can say is that from the technology standpoint, the technology maturity of CCS is good, and we could, I mean, this is a technology that has been proven onshore for the capture part, offshore for the storage part. So it's a mature technology, but I think the challenge with this activity is mainly cost. It's cost driven, and today those projects are not economical. That's as simple as that. As long as we don't have a CO2 tax, which is higher than what it is today, I don't think there's a lot of value for the companies to go into the CCS project. So I think we need stronger constraint from the government on the tax of the CO2 for a company like Vår Energi to go into this business.
Yes, we can, based on some of the examples we've shown today, we can say that there's incentive to make monitoring solutions simpler and more agile and less complicated, less heavy, let's say, even though we still need to take into account the physics of the monitoring as well. But you're right in the sense that there is a big part of it which is the cost.
Yeah, and
I have a comment as well. Sorry, do you want to go, Fiona?
Yes. Yeah, no. I mean, you go ahead, Catalina.
Yeah. So there are two parts of this question, because the monitorability is a must. If we don't prove that that the project is, or the CO2 is monitorable, then we cannot have a project. So you have to come up with a solution that is capable. You have to come up with a solution and demonstrate to the government that you're capable to monitor where your CO2 is going. Having said that, of course, as the gentleman from VOR just said, CCS projects are not as cost efficient, or no, they are not. They don't give as much money as the oil and gas business. So we have to be very creative as to what kind of monitoring techniques we use. So, for instance, for the Northern Lights, we had evaluated quite a few monitoring alternatives, as I showed in the presentation. But one of the ones that we also evaluated was whether we could do OBN or whether we could do permanent receivers on the seafloor. And of course, that's not cost efficient or cost effective. There is just not enough money in the CCS business to do that. So you have to go with the minimum possible, but that can still satisfy the regulations. And that's why Gravity and CSEM was a potential, they were potential monitoring techniques that we evaluated, and they just didn't work for our case. That doesn't mean that it's not going to work for others. Also, we're still hoping to use DAS, which is a cheaper version of a seismic survey, and that has worked for other CCS projects where doing a 3D seismic is forbidden, is economically not feasible. But in the case of Northern Lights, at least, the best solution is seismic, and what we have a baseline now that is very big, but the reason we have it big is because it's a baseline. For the repeat surveys, they're going to be smaller, and they are going to be tailored to what we find in the first repeat. So if the first repeat tells us that the CO2 is not moving fast enough, then you don't do a repeat in 1 year later, which is what we thought we would do. So you have to make sure that you monitor and that you tell the government that you have a handle on that, but at the same time you have to do it as cheap as possible. It's not an easy conundrum to solve, but it is the situation where we are, and yes, we are always evaluating cost. I don't know if that answers the question.
Can I ask you a question? Following up what you've just said. So if you are looking at money, what were you looking at with the CSEM as objective? Seal integrity or plume size?
Plume, hopefully. I mean, that's the monitoring, the most important part in the regulations. That's like one of the first things they want to know is, do you have a control where the plume is going? Of course, it's very important to know whether you are.
Where you can get that through seeing if the seal gets breached. But the question is, the value, the money value, comes from the size of the plume. But Svein presented us his CSEM, and he looked mostly at the parts where the seal was being breached. So those are very, very much different problems for CSEM.
Yeah, and I guess, yes, that's fine. And that's
I'm
fine.
asking this because you're concerned about the cost, because there's nothing cheaper. There's nothing cheaper than doing CSEM compared to seismic. So if you are concerned about the cost and you pay 10% more than seismic, or you do 10% less than seismic. So, but of course, it depends, horses for courses. I don't know what you did with the CSEM modeling. What I have seen from the Northern Lights CSEM modeling, which is published, it only shows that CSEM doesn't work because you're looking at 5 to 15, 20 years and you don't have anisotropy in it. And it says it works, and you say, yeah, it works, but it doesn't work good enough. So it all really depends on what you want to do with it.
May I
So if
answer
you
your
could
question?
point me in the direction of references where I can read that up, I can maybe ask some more
The
questions.
feasibility study that was done for CCM has not been published.
Has not been published.
No, that has been work done by Shell. They did a feasibility study on the two types of sources that we have, the two types of methods that we have for CSEM. And as I said, we would have loved to use CSEM. I'm not discarding it as a tool for monitoring. It's just that based on that feasibility study that is not published, did not yield good results for the type of depths that we have and the saturations that we expect.
Yeah, well, my experience
but
is
it might work for others. I'm not saying that it won't work.
My experience is that all of these geophysical methods, in particular when you're going down to the reservoir itself, have very equivalent answers unless you are calibrating them against the borehole log. Because the borehole is as ground truth as it gets. And even the borehole log can be up to 40 to 50% wrong. So I am almost questioning anything that's being measured from the surface for the purpose of monitoring, unless it's properly checked and reviewed and everything else. And it doesn't matter who produces it, because you just don't have enough information to see what is happening in the reservoir unless the borehole tells you and the fluid substitution of the borehole tells you what values you really have. Because you are influenced by the overburden as well as the reservoir, as well as all the sites. There are too many influences. There are too many options.
That's correct. That's correct. And that's why all these evaluations, they need to be carefully matched with a rock properties model that usually comes from wells, yes. But in CCS, we only have 1 or 2 wells at a time. So if you are going to monitor the CO2 plume behavior in 25 years, you cannot rely on just one well. And the well does have monitoring. Of course, you have to have pressure gauges and temperature gauges. But we're talking about a spatial aerial distribution of the CO2 plume. And
why you need the calibration points.
But we have the calibration point by the one well or the other wells that are being input into the rock property model that you use afterwards to make sure that you've to tie the loop, the history match and so on. That's not a problem. But you just don't have a lot of information, but you do what you can do with what you have. I mean, there is no other solution. You can't put wells all throughout the plume traveling. So the idea, of course, would be to have an observer well somewhere and then do lots of DAS. But that's also not cost efficient.
I'd like to add some fire to this discussion as well. Sorry, go ahead, Kurt.
Yeah, I'm just concerned. I mean, we're talking about not having any money and saving money, and then we discredit with a single experiments on electromagnetics where we have at least 40 or 50 different options to use different ways to looking at the same volumes. And we discredit a complete method, and the work that is putting this out there is confidential. And after 40 years, I've only seen one survey in 40 years all over the world where EM really didn't work. And everybody else, as bad as some of the surveys were, they were always somewhat right. And the work I've seen from Northern Wells, let me just say one more thing.
Don't put words in my mouth. I didn't say that it was confidential. I just said it hasn't been published. It could be published if somebody who goes and does the work of publishing it, but we haven't done it. So
yeah, well, it needs to be peer reviewed. I would very much encourage that it needs to be reviewed. Because what I've seen from the Northern Lights is the work done by Parkes, published, EMGS, which unfortunately has 2 big time steps. and it shows that CSEM can see something. It is so broad and it doesn't have anisotropy in it. So it doesn't have the resolution to be of practical consequence, but it does show that CSEM itself works. And so if you want to save money, then you want to use techniques that are cheaper. And if you want to save money, you can improve those techniques and not just say, as we go and spend more money on something we know has less sensitivity to fluid movements. Because we do know that seismic has less sensitivity to fluid movements. So anyway, I just wanted to say that.
And if I can add to that discussion, the cheapest of all methods for this, well, for any kind of monitoring would have to be 4D gravity. It's also probably the most socially acceptable as well, since it's passive measurement.
Except you need ball gravity.
Well, that would be better, of course, but that gets more expensive then. But I have even done some modeling studies based on the reservoir model where it is large time steps, but you can track the front movement fairly well, even at 4 kilometers subsea, which is greater than Northern Lights. So I think it's possible. It'd be desirable to find a way to make that work, at least to the satisfaction of the regulators, if it's at all possible.
But Anthony, you're talking about,
and I agree with you that the gravity would be a fantastic tool, and we see it working in many other fields. For us, and it's just for phase 1. This was a feasibility that was done for phase 1, meaning the well EOS that is located about 10 kilometers or 8 kilometers from the license to Troll, and that's our border. That's our boundary. It means we cannot allow for CO2 to migrate outside of the license. So when we say that gravity for us didn't, in the feasibility study that was done in Equinor, it said that it might, not that it didn't work, but it might tell us information when it's already too late, when we have already crossed the license. So the monitorability has to be in such a way that you can react immediately and stop injection if you think that is the CO2 is going somewhere that is considered a leakage. And that's why the gravity was not considered. But I think I totally agree with you. This is a fantastic methodology, and I would encourage anybody that is in CCS to do their own feasibility and see if it works for you. And one thing that we haven't done is to find out if with the new distances that we have for wells in the phase 2, since those wells are going to be farther from the border, if maybe we can use gravity to monitor those. We haven't done that work.
And a follow-up question, if I can, then, in the determination of whether it works or doesn't work, was that a qualitative assessment, just looking at the map changes of gravity, or was it a more quantitative assessment, given all the other seismic and well constraints that you already have, doing a quantitative inversion, because that might improve the performance of 4D gravity substantially, I'm guessing?
So that work was done by Anna Kari Fure in Equinor, and I believe it was a more quantitative assessment. I was not there in the project when this happened, but I encourage you to contact her and ask her exactly how she did it. Again, this is one of those things that we do in the Northern Lights and not necessarily require a publishing. To publish things requires work, and if you are completely saturated with work yourself, then you really you put effort on things that have more meat in it, and just a feasibility studies might not be considered at the moment or at the time enough meat to publish it. So this feasibility study that was done for the CSEM was assured by the quality, the technical assurance in Shell, and it was done by CSEM experts in Shell. So the gentleman that was advocating so much for this technology, I can pass on his email address if you want to have a proper chat with him. That's all I can do.
If I may, yeah.
So
no problem.
John has his hand up there.
Sorry, go ahead.
Okay. No, I just wanted to add a couple of comments to the discussion. One method that can be used to easily forward calculate 4D gravity is basically just to use the reservoir model simulations and do the calculation on those, and then you will get the 4D gravity response just by using the Newton's law of gravity as the transfer function. So it's extremely simple, and it will give you a very reliable result on how the continuous gravity signal will look like at the seabed at any given point of view. Yeah. The other comment I wanted to make, just I saw Kurt Strack mention that the borehole gravity will be the way forward. I would just, if you are to place permanent gravity measurements in the borehole, you will have the problem of drift. If you want to repeat measurements in the borehole with on the wireline, you will have the challenge of being able to get very precise tilt when you are doing the repeat measurements. And up to time, I haven't at least seen very stable ways of performing these measurements. But I agree that it's a nice thought, but at the moment I have not seen technology.
Well, maybe
that
give you the
allows...
answer, because we stopped those projects 20 years ago after spending $15 million. First of all, you assume that you measure gravity the conventional way. So 20 years ago, we looked at making thousands of downhole permanently in place gravity sensors to get down in the reservoir, because 1 microgal resolution at the ocean bottom is insufficient to monitor fluid variations in the reservoir itself. And that's what any 3D gravity simulation shows you. To make a long story short, for $100 million, you can have a system like this. And we stopped it because it's totally unacceptable price. Because you cannot make technology and provide services with a technology development like that. And because it doesn't only cost $100 million, but it also takes 15 years. And we did this with many oil companies involved and many major service companies involved. And we used essentially gravity measurements on an optical basis so that we could stack thousands of measurements to get the resolution down through stacking, because the maximum accuracy of measurements in the borehole you can get is 5 microgals versus 1 microgal at the surface. So you are trying to find an anomaly that's much smaller than 1 microgal, as you have shown, and there's nothing you can do. So the only way you can do that is use geophysics, which is signal averaging and spatial averaging, just like you do in seismic. That's the only way to get gravity to the point where you can do it. And you can also need directional sensitivity in gravity. You can do all of that, but you can't build the hardware. And so that's when we stopped, and many companies have asked me many times to start it up again, and I'm not going to, because I will be dead for decades by the time the project is done. So it's very complicated to make those type of sensors, but you can do it. The Russian military has one.
Are you speaking of Lockheed Martin's proposed system, Kurt?
Well, they were doing the feasibility, but that's not it. As you're essentially mixing absolute gravity, what Lockheed Martin proposed was another alternative, not the one that the system that is on the market. But yeah, Lockheed Martin was involved, but for different sensors.
All right.
And they have the patents now, by the way. But we stopped this 20 years ago. So it takes a lot of money.
I think Cedric's had his hand up for a little while. Cedric, do you want to go ahead?
Yeah, thank you. I had a question for Catalina. I mean, this Northern Light project is the project we have in Norway. So it's getting a lot of attention, and I assume you need to use a lot of matured technology for the monitoring part. At the same time, it could be a fantastic laboratory for testing also cheaper methods as well. So do you have a plan for that?
Actually, well, yes. Yes and no, I guess. Or yes, so one of the monitorings, and this is not really geophysical, but one of the technologies that we would like to use in the future, and we don't know if it's going to work yet, is to monitor for potential leakage of gases into the surface. And there are, of course, already systems in place for having ROVs to go on the seafloor and capturing gas samples. But there are, of course, quite a few initiatives beyond that. So there is one by which they capture the samples and they analyze the isotopes immediately. So in that way, they tell you whether you're looking at the CO2 or you're looking at methane. And if it's methane, then there is no worry, right? But if there is CO2, then you have to worry about it. And the other one is to have an ROV that actually is a smart one, and instead of going on a grid and maybe miss potential gas escapes, they would have an ROV that smells where the gas emission is happening, and then they would do a smart path around it, collecting more samples. So that is something that has been proposed for the environmental monitoring, because we don't only have to monitor where the CO2 plume goes, but we also have to monitor for potential leakage that you don't see in the seismic, correct? And that would be one way to do it. And in the NEA application, which we have to apply this for this year, there is a space there where you can offer or you can propose new technologies, and this would be one of the ones that we are going to propose. But yes, you're absolutely right. All the eyes are on us, and that is one of the reasons why our baseline is quite big. The first options were to make a baseline that was smaller, and then make kind of a baseline that grows with time as the plume moves. Then you make an extra baseline with a repeat survey all included in one. But the owners, the partners didn't like that, because of all the perception of so what if something happens, then you don't have the baseline to go back to. There is a lot of the government has their eyes on us more than in any other oil and gas project, which is quite new to us, and therefore you have to come up with, as I said before, with a technology that is not too expensive, but at the same time fulfills the government requirements.
Thank you.
Yeah.
Yeah, I think I just follow. Yeah, I think it is very much the thing is there's like what you could do from a technical perspective, and like you could do your risk assessment, and you can say, look, there's no way any CO2 is ever going to get through this section of overburden. So do you need to monitor it? But of course, there's the technical part, and then there's this public perception part. And I think until CCS is more mainstream, it's going to be sort of hard to move away from that need to sort of fulfill the sort of public part. And also in terms of regulators, I mean, obviously Norway actually has quite a few projects compared to everywhere else in Europe. But I know no other country in Europe has really got active CCS yet. So regulators are, quite nervous, and they don't, they know that they don't know everything. And so, and because they are actually still really the oil and gas regulators, they are very used to like seismic, because seismic has been the thing. Seismic's what they like to see, and so, and that's the hard thing. So I think, but it does show that, we really need to get other technologies onto projects somehow, and in a way that data can be publicly shared and publicly released, to build the confidence that like we can monitor without, loads of massive 4D sites. And I'm coming from a seismologist, but still, without loads of massive, huge 4D surveys, there is and I think part of it is as well the fact that sometimes studies are done, but so little of the data can be publicly released. That also makes it, that also makes it difficult. So yeah, so I think there's a lot of sort of room to move in the monitoring space to come up with better solutions. Thank you very much, Catalina, for joining.
We have a hand up by Habib. Do you want to add? You also had a question earlier on.
Yes. Thank you, Emin. Yes, in fact, I would like to ask you to all the audience the question about synergies. It was just been mentioned by Northern Light that they are let's say investigating solution with ROV capable of sniffing the surface. But is there a way to synergize the use of equipment? Let's say, for instance, to deploy a small receiver, seismic receiver, on top of an electromagnetic measurement using the same, I will say, boats, or the same, you know, to let's say to make let's say, to stop with the old habit of the oil and gas to have dedicated vessel for seismic, dedicated vessel for CSEM, and so on. Because what we saw in most of the presentation is that we are all aiming toward lighter solution. So my question is, do you think it is achievable as an industry, or is it just
the equipment exists? The Brazilians are reinventing it, so you will hear about it. But the equipment of marine seismic and EM system exists, and the equipment for land exists for a long time. We have been offering this for over 10 years, and people aren't buying it. And now some people are starting to do that for volcanic research. And it's a matter of education and what people know and what they don't know, and whether they do it and don't do it. But the equipment exists. So the equipment is there, but people aren't using it.
Yeah, but because let's say for passive seismic, maybe it's not enough. For active seismic, if you want to provide an image, it's too, let's say, it's still not enough. But for our kind of approach, it's worse. I mean, I just need one or two or three, and my job is done on the receiver side.
Yeah, but you can look. It's just a matter of what seismic sensors you select and what EM sensors you select. Both exist, and both of them are commercial, and they are manufactured in any quantity you want. So it's a matter of somebody applying it. You need to find a problem where the value is high enough, and you need both types of information. The problem is that EM works best when seismic doesn't work. So that's what people do. And when seismic works really good, seismic is so much better than anything else. Why the hell do you want to do something else? So that's what we live with. So you need to do a research project where you take the risk of doing both. But the equipment and the methods are not a problem. The technology to combine the interpretation has been published many years ago. It's not proprietary. Anybody can do it. It's very simple mathematics and physics. So this is all available.
It's always
yeah. There. That's okay. We are now testing electromagnetic nodes, and we are actually attaching OBNs under it to check out if they interfere. Because if they interfere, it might be disturbed. But if they don't interfere, you can in principle go out on an EM survey, bring 400 nodes where you have OBNs attached under it, and you can drop it, and you can do a measurement of seismic and also CSEM or MT. I will not recommend to actually total source at the same time, but if you want to, for instance, do full waveform inversion with refraction seismic, then you don't need to have a distance that is shorter than 1 kilometer. And then you can use it both. And if it's on deep water, you can actually pop it up by acoustics, you don't need an ROV. So there are possibilities to use this. But as Kurt said, it's many people have done it before, but this is Alton's approach. So we will test it out and find out if it's interfering with each other.
Thanks, Sven. Thanks, Habib. Do you have any other questions? Because actually, the question you asked was interesting. I wanted to ask a similar question from Svein, and we also answered that. Because working in an old company, yes, we can make a business case to test that on this technology and take it forward and test it. And actually, so also Cedric mentioned earlier on, projects like Northern Lights, or let's taking back to, for example, Jonas Sverdrup, even for the monitoring as well. We did test quite a lot of different approaches there to try to come up with the best approach in the long run. And then taking this idea that we need to, for the CO2 monitoring, we need to achieve a cost-efficient and optimized solution for monitoring. This sort of view of various approaches, having like a big box and you explore the box and see what brings you, what you actually will stay with. Maybe it's not the only solution, but you will, like what Habib says, you can do that. You take one solution and then you monitor it frequently, but you take maybe a larger one for a certain interval. But that's sort of the idea. It would be interesting to hear from the contractor companies. What is that you would like to do, and how would you like to take it forwards? How do you want to sell it, or how do you want to achieve these results that you think the technology will bring the value? And we have another question from Maria Maquette. If you want to unmute yourself and ask your question, I can also read that question. It was for John.
Yeah, hi. I was for John about the gravimetry. I'm sorry, I'm not very familiar with the gravimetry, but I have trouble to picture the sense on what's the relation between gravimetry and depth, and how can you differentiate between, I don't know, I'm going to say 1 million, but 1 million tons confined in the reservoir and 1 million tons confined in both the reservoir and a vertical leak. Is that making sense?
Okay. Thank you. I will try to. I mean, when we are talking about the magnitude of a 4D gravity signal at a given location, what is defining this magnitude is basically depending on the actual mass changes happening in, for instance, a reservoir, and also the distance from the location where you are measuring and where these mass changes are happening. If we have a situation where CO2 is migrating vertically upwards, we will have a situation where masses will come closer to where you are measuring, and what will happen then is that you will get the elevated signal. So if 1 million ton is moving upwards, that will at a given depth generate a signal. So that, and again, that's very easy to model, how much volumes you need and at what depth it needs to be before you are able to see it. But another thing that's also interesting with CO2 is the fact that most of the times you're looking at projects where we are injecting CO2 in a fluid phase. But when you are moving upwards and the pressure is going down, you will at some certain point the fluid CO2 will go over to gas phase, so it will have a significantly different density. This will also generate a very, very significant signal for that you can observe on time-lapse gravity. Did that make sense?
Yeah, sure. So I guess there is also the trouble of uniqueness of the solution. Two different reservoirs can give you the same gravimetric response, right?
Yeah. So what you're asking is if you are measuring at a given location, and then you have changes in mass happening at different levels. Is that what you're asking?
Yeah. I mean, like, for example, two reservoirs at X and Y depths can give you the same response as a reservoir at like Z depths, right?
Yeah, I mean, at the end of the day, the method is able to measure the total changes in mass, right? And if things are happening at different levels, then you need to kind of either tie in other methods, like for instance, we have heard here about doing seismic at the dedicated spots, like Habib was presenting. Then you can actually measure and actually see where changes are taking place, because 4D gravity does not have the power to differentiate in in depth, unless you can actually use your reservoir model to identify. So maybe the reservoir model is and the 4D gravity together can help you disentangle where the effects are stemming from. But obviously that must be evaluated on a case-by-case basis. But we do, of course, some of these modeling exercises where we try to control mass changes at different levels, and you are depending on, if you're going to do it kind of a standalone with only 4D gravity, you are depending on including all the detailed information from the reservoir model in the interpretation. Yeah.
Thank you.
Maybe I can make some interesting comment, not necessarily answering this. I saw 2 weeks ago a microseismic image of a CO2 reservoir when the reservoir was breached and the CO2 moved, and then it stopped moving. So what, and I don't have it handy, so I can't show it, but Microseismic Inc. has some of these. And so what happened is within 30 minutes, and only within 30 minutes, and they were looking at monitoring for months and months, but 30 minutes within those months, the reservoir was breached, the CO2 moved upwards through the reservoir breach, and it got stuck at another layer above and moved then to the side and then disappeared again and settled again. So you had essentially an anomalous behavior for 30 minutes inside of the reservoir. So what really should be concerning the regulators, and I hope there's no regulator listening in here, requires much, much more resolution than what we are looking at with geophysical methods these days, because capturing some 30 minutes within a few months or something, and then capturing it with directional sensitivity is extremely difficult. So think gravity in the M under those conditions, almost impossible.
I think it's difficult to comment on that case, Kurt, without having read the paper or understanding what other types of data that was collected. But thanks.
But I agree with you on the fact that I think we should forget about what we should still keep in mind what we learned from oil and gas monitoring. But I agree with you, Kurt. The thing is we need to prevent any leak, and if the leak is happening within a week or within 30 minutes, like you are saying, then whatever the monitoring technology we have, or all the monitoring technologies within us we have, it needs to be agile enough to adapt and to catch this kind of leakage or weaknesses or threats. So I don't have the solution for that, but I think a mix of monitoring agile technology could be a solution.
Thank you, Habib. I think that's a nice comment, perhaps, to try and bring this workshop to a close. But before I do, are there any other questions or comments outstanding? Anything I've missed in the chat or the question window?
No, there's a hand from Bruno. Please go ahead. It's like a help confusing.
Okay, then. Well, I'd like to again extend our thanks to all of our speakers. A very interesting and very nice setting of the discussion from Catalina at the beginning, and a nice overview from Cedric from VAR. Some very provocative comments and very interesting commentary from Kurt, as always. It's a pleasure to have you with us, Kurt. A nice overview of the 4D gravity situation and what's possible now with improved technology in terms of those accuracy numbers. Thank you, John Evan. Good, solid presentation from Sven, as always, on the CSEM side of things. And I think it was nice to close with the presentation from Habib talking about combining these techniques, which is a discussion I'm certain is going to be ongoing as we move forward here. Whereas, yes, combining the different techniques, I feel, would certainly bring more rich information, probably possibilities for optimization, not just of cost, but also of what's possible in a short period of time as well. Thank you to the organizing committee as well. Everybody put in quite a bit of effort to bring this together. It's a rather shorter workshop than the last one, but I think the focus made it that much more interesting on these techniques. And lastly, and certainly not leastly, is Laurie's help in organizing this from the SCG. Fabulous job, Laurie, as always. Thank you. We couldn't have done it without you, and get well soon. Still open for any other comments or points anybody else would like to make. But in the absence of that, thanks to all again, and we'll close this workshop and look forward to the next one.
Thank you very much. Thank you, Anthony. Thank you to everyone
very much.
contributing. Thank you.
Thank you.
Thank you. Bye.
Bye-bye.
Bye-bye.
Thank you. Bye-bye.
Thank you. Bye-bye.